In this session, I'm sorry, there is some technical issue was there, yes. Alright, so guys, welcome to the session. My name is Dr. Shankar Sir and I am your physics educator. So in this session, we are taking further the properties of solids. So in the last session, guys, what we have spoken about. So in the last session, what we have done. So in the last session, we have talked about the uh, cases in which a body is subjected to an axial load like this. Okay, okay, and we have seen that how we can apply. बेटा मैंने फिर मैकेनिकल इंजीनियरिंग में एमटेक और पीएचडी किया ना, मेरा इंजीनियरिंग में इंटरेस्ट था, समझ रहे हो? ठीक है, इसलिए मैंने बीएससी एमएससी नहीं किया है, मैंने एमटेक किया और पीएचडी, बीटेक किया, एमटेक किया, पीएचडी किया. गेटिंग माय पॉइंट? ठीक है, चलो एनीवे. सो लास्ट सेशन में गई हमने इसकी बात की थी कि सर अगर किसी बॉडी पे कुछ इस तरीके का लोड लग रहा है तो आप इसको कैसे डील करोगे, इसमें लॉन्गिट्यूडनल स्ट्रेन, लेटरल स्ट्रेन क्या आएगी और स्ट्रेस क्या आएगी. तो इसमें हमने सीखा कि स्ट्रेस होती है फोर्स अपॉन एरिया एंड इलोंगेशन होता है पीएल अपॉन एई, राइट, है ना, फ्रॉम द हुक्स लॉ, है ना. ठीक है, आर यू गेटिंग माय पॉइंट? तो ये बेटा हम लोगों ने लास्ट सेशन में ये बात देखी थी कि भाई इस तरीके से हम इसको यूज कर सकते हैं और इसी की मदद से बेटा फिजिक्स, इंजीनियरिंग फिजिक्स का ही क्या है, एप्लीकेशन है. और क्या है, व्हाट इज इंजीनियरिंग? इंजीनियरिंग इज द एप्लीकेशन ऑफ फिजिक्स. आर यू गेटिंग माय पॉइंट? ठीक है, फिर मेरा रिसर्च में इंटरेस्ट था तो मैंने रिसर्च किया. आप मेरा नाम गूगल स्कॉलर पे लिख करके देखिए, आपको मेरे रिसर्च पेपर मिल जाएंगे, है ना. इंटरनेशनल रिसर्च पेपर है बेटा मेरे. Are you getting my point? ठीक है, इंजीनियरिंग फिजिक्स का ही एक ब्रांच है. फिजिक्स से ही नहीं, फिजिक्स अपने आप में बहुत बड़ी चीज़ है ना. मतलब आपको जब आप रिसर्च पे जाते हो तो आपको उसको कन्वर्ट करना पड़ता है, आप किसी छोटे डोमेन में करना पड़ता है. एनीवे, जब आप उस एज में आओगे तब आपको ये सब रास्ता मिल जाएगा, डोंट वरी, है ना. तो चलिए कंटिन्यू करते हैं. तो लास्ट सेशन में हमने क्या बात की कि अगर किसी बॉडी के ऊपर इस तरीके का लोड लग रहा है तो उससे स्ट्रेस क्या आएगी और उससे इलोंगेशन क्या होगा, डिफॉर्मेशन क्या होगा. ठीक है, ठीक है. तो सिग्मा इज इक्वल टू पी अपॉन ए एंड डेल्टा इज इक्वल टू पी एल अपॉन ए, है ना. और इसी की मदद से फिर फर्दर हमने क्या देखा, हमने देखा कि भैया बॉडी में स्ट्रेसेस, मतलब हमने देखा टेपर्ड बार का केस देखा, राइट, कि अगर मान लीजिए बॉडी हमारी टेपर्ड हो जाए. फिर हमने सेल्फ वेट का केस देखा, है ना. हमने सेल्फ वेट देखा कि अगर एक हमारी यूनिफॉर्म क्रॉस सेक्शन की बॉडी है उस पर कैसे डील करना है, अगर हमारी एक कोनिकल बार है तो उस पर कैसे डील करना है, राइट. ये चीज़ हमने देखी. और हमने क्या देखा लास्ट सेशन में, और हमने देखा कि अगर यंग्स मॉडुलस भी वेरिंग हो, अगर यंग्स मॉडुलस वेरिएबल हो तो उसे कैसे डील करना है, पॉइजन रेशियो को कैसे डील करना है. तो ये सब बातें बेटा हम लोगों ने लास्ट सेशन में की थी. ओके, ओके, एंड आई होप आपको ये चीज़ें समझ में आई हो. तो अब बेटा मैं आपको एक कॉन्सेप्ट और बताना चाहता हूँ यहाँ पे, बार्स कनेक्शन का. तो बार्स कनेक्शन मतलब क्या है, बार्स इन दो तरीके से आप कनेक्ट कर सकते हो, एक सीरीज में, एक पैरेलल में. ठीक है, एक सीरीज में, एक पैरेलल में. ठीक है, देखिए इस कॉन्सेप्ट का भी काफ़ी यूज़ होता है. मान लीजिए आपकी कोई बॉडी है, उसके ऊपर बीच बीच में लोड लगा दिया जाए तो ये आता है. देखो मैं समझाता हूँ. मान लीजिए आपकी कोई बॉडी है, देखो, ठीक है, मान लीजिए आपकी कोई बॉडी है. तो अगर बॉडी पे कुछ ऐसा लोड लग रहा है, ये पी है, तो आप कहोगे सर भैया इसमें तो हमको कोई दिक्कत है नहीं सर, ये तो हम सीख चुके हैं, इस केस में हमें बहुत आसान लगता है, हम स्ट्रेस भी निकाल लेते हैं, इलोंगेशन भी निकाल लेते हैं. बट व्हाट अबाउट कि अगर मैं इसी बॉडी में बीच बीच में भी लोड लगा दूँ. मान लीजिए एक लोड मैंने यहाँ लगा दिया, 2p लगा दिया, एक लोड मैंने यहाँ पे लगा दिया, मान लीजिए इस डायरेक्शन में 6p लगा दिया. आर यू गेटिंग माय पॉइंट बेटा? ठीक है, तो इस केस में मान लीजिए सबकी आपकी लेंथ वगैरह आपके पास है, मान लीजिए ये है L1, ये है L2, कुछ भी लेंथ दी हुई है आपको, और ये है आपका L3। ठीक है, तो हमारे पास क्या है, L1, L2, L3 है, ये है A, ये है B, ये है C और ये है D। ठीक है, तो आपके पास ये सब है। अच्छा, बहुत बढ़िया। ठीक है, तो अब देखिए क्या है, सो व्हाट इज देयर, सो एज आई वाज स्पीकिंग, सॉरी आई वाज कम्युनिकेटिंग इन हिंदी, यस फॉर योर, I'll just repeat myself, sorry. So in the last session guys, we have spoken about this thing. Okay, we have spoken about that when a load is acting on a body, what is the stress, okay, what is the elongation, what is the delta, right? About it we have spoken in the last session. So when a body is subjected to a axial load of P, then the stress that is equal to force upon area, and it is also called as the normal stress. So this normal stress comes in the body, and due to this there is an elongation of the body given by PL upon A, right? So in the last session we have seen, we have analyzed these equations, along with we have done some special cases like the tapered bar case, like the self-weight case. If the Young's modulus or the elastic property is varying, that case also we done, Poisson ratio we done. So we have done it in the last session, this much, right? Now we are in today's session, we are going to deal with one new and very interesting and very useful topics, that is bars in series. Okay, I'll call it bar connection. Okay, so I'm going to tell you a shortcut way that is going to help you a lot in solving such kind of questions, right? Now see, please understand this. So this is, let's suppose, a problem. Now we find these problems very easy when the load is at the very end of some bar, right? Okay, but what happens now when the load is acting at different points within the body? Okay, like for example, in this case, you can see that load is acting at different points on this very body, right? Now, how you can approach it? Yeah, they were obviously big people. Okay, there are many such examples. So anyway, let's try to understand this concept. So we are having in this condition, so how this is first of all different from what we have learned. So I hope that right away when you see the problem, or you see the statement, problem statement, you realize that, sir, this is how it is different from it, right? So in this case, there are multiple forces acting on the body at different locations. Now, what is the first step that you must do to solve this? So the first step for you to solve this is find the reaction. See, in the books you may see that they are solving it on the basis of, free body diagram, but I am going to give you another way. The first thing that you have to do is find the reaction. What you can do, you can find out the reactions. So first of all, you find out the reaction. So see, how's the finding out the reaction? So we'll be using this equation. Okay, sigma fx is equal to 0. Okay, now what is sigma fx is equal to 0? So we know on a body when many forces are acting, the summation of the forces in any given direction, the summation of the forces in any given direction, the summation of the forces in any given direction must be 0, and the summation of moments also in any direction must be 0. Okay. Okay. So now using this equation, we can find the first thing, that is the reaction. So how we can do it? Now see, now see what is the, see, very simple. You don't have to take much pain. What is the net loading on this body? What is the net external load? So we can see the 6p is acting in this direction, 3p is acting in this direction. So can we say that 3p is the net load which is acting in this direction on this body as a whole? Okay, so when you see this body as a whole, what you do get, you get that the load is 3p in this direction, right? If you see 6p, 2p and p together, you can find that the load is 3p in this direction. Now load being 3p in this direction, what is going to be the reaction? So the reaction will be 3p in this direction. See, reaction is always equal and opposite of the net loading. So the first step that you have done, you found out the reaction. I hope it is fine to everyone, right? Now, once the reaction is found, the next step you can do. So now many people approaches it with the free body diagram. I don't prefer that. So in the next step, you must be making the axial loading diagram. You must be making the axial loading diagram. Okay, so with the help of axial loading diagram, once the axial loading diagram for any problem is made, that problem is going to be ultimately very easy for you. Okay, so axial loading diagram. So for making axial loading diagram, we'll follow some sign convention. Okay, and we always move from the left hand side. Okay, so these sign convention that I am taking are valid when we are doing the things from the left hand side. So see, if we start, what do you mean by left hand side? So if we start from A and we go to D, okay, so from A to D, from A to D, from A to D, that is what we know as the left hand side, LHS. So from left hand side when we are moving from A to D. We are moving from A to D, right? Okay. So see how it is so simple to make the loading diagram. See, I'll be taking the sign convention. So what are the sign conventions? From left hand side means from the leftest point to the rightest point we are going to move. Okay, so in axial loading diagram, we are going to follow these sign conventions. So this is we are going to take as positive. This we are going to take as negative. Whenever I see this direction, I'll take as positive. Whenever I see this direction, I'll take as negative. Now see how simple it is. So we are going to make a baseline, or you can call it a datum line. So this is your datum line. Now this 3p that you are having, so this 3p will be, so this is the sign. So you make, not to make any mistake, you make the sign here. This is positive, this is negative. Now when I see this 3p, this is a negative, so I'll move in the negative side. So it is going to be the 3p. Now till the application of next load, okay, so you have to move by a straight line from this point till the next load is applied on this body. So this is 3p in the downward direction. Now I move to this point, and this is 6p. 6p in this direction. So 6p in this direction, that is minus 3p plus 6p, minus 3p plus 6p. So it will become plus 3p. It will become plus 3p. Now till the application of next load, it is going to be the straight line. Till the application of next load, it is going to be the straight line. And now at C, now at C, what is going to happen? Now at C, this is 3p and this is at C. So at C, what is going to happen? So till the application of next load, so see, you just have to do the same. So I'll just do again. So see, I start with A, I see this direction, I consider is negative. So this is going to be 3p. So above this line, we'll consider positive, below is negative. Now from this point, we'll start with a straight line. Okay, and till the application of next load, we'll move by the straight line. Now this direction, when I see, this is positive. Now minus 3p plus 6p will become how much? Minus 3p plus 6p will become plus 3p. Now till the application of next load, we'll move by the straight line. Now this is plus 3p and this direction is negative. So plus 3p minus 2p, that will become p. Now till the application of next load, we'll move by the straight line, and this is plus p and this direction is minus p. So plus p minus p will become how much? It will become 0. I hope it is fine to everyone. So basically this is what we call as the axial loading diagram. And once the axial loading diagram is made, and this is so simple, no? So we are making free body diagram, we are seeing this side, that side, so many concepts, we are getting confused, we are making silly mistakes. No scope of silly mistake in this. See, you just have to move with the load. Wherever you see one, you include that, right? That's all. Okay. Okay, and good thing is that from this method, you'll always get an indication that whether you are approaching the problem right way or wrong. Because see, in loading diagram, in the axial loading diagram, you are going to see, that the last point always becomes 0. Okay. Okay, the last point of the loading diagram will always become what? It will always become the 0. Understood? Okay, so here the last point of the loading is becoming 0, so that means your loading diagram is correct only. Okay, now once the loading diagram is made, so once the loading diagram is made, what we can do? See, now once the loading diagram is made, from the loading diagram, you can see from the loading diagram, you can see that so each section, once the loading diagram is made, instantaneously you get an idea or you get the information about the load in each of the section of this body. Like for example, in the AB section, what is there? In the AB section, the load is minus 3p. The load is minus 3p. In the BC section, see, says how you are doing it. So see, in the AB section in loading diagram, you will see a sort of rectangle. So in the loading diagram, when you are seeing one rectangle, okay, the height of that rectangle is going to give you the load in that particular part of the section, right? Part of the body. Right, so in AB part, I can see that we are having a rectangle whose height is minus 3p. Okay, so it is, sorry, I'll write load, load in the AB section. So load in the AB section is minus 3p. Right, now what is going to be the load in the BC section similarly? So load in the BC section, it becomes, see how much in the BC section, I can see one rectangle whose height is plus 3p, and in the CD section, the load is plus p. In the CD section, the load is plus p, right? Now, once the load, so see, first of all, you find the reaction, then very easy steps, you can make the loading diagram. From the loading diagram, instantaneously, you come to know that what is the load in every particular section. Now, once the load in each of the section is known, you very well know your formulas. Sir, once the load is known, so sigma AB is equal to PAB upon area. Sigma BC is equal to PBC upon area, and sigma CD is equal to PCD upon area, right? Okay, so what it will become? It will become minus 3p upon A. It will become plus 3p upon A, and this will become plus P upon A, right? Easy. Any issue in this? No, sir, not at all. Now see, now see, what will be the elongation of each of the sections? So, sir, AB section, the load is minus 3p. Length is, let's suppose, L1 upon AE, because area is same. Right? In BC section, the load is plus 3p L2 upon AE. Okay? And in CD section, it is going to be, see, in the CD section, we are going to have PL3 upon A. Okay. So ultimately, once the axial loading diagram is made, you know the stresses in each individual section. You know very well the stresses in each of the individual section, and you also know the elongation of each of the individual section, right? Now, if at all it is asked to you that what is the net elongation, what is the net elongation or the elongation at point D, so you are going to add the elongations of each of the individual sections. So when you add them, you'll get the net elongation. And remember here, see, it is coming out to be minus. So this is compressive in nature. Minus refers to compressive. This is the sign convention we are going to follow. This is tensile, and this is also positive. So this is tensile. I hope it is fine to everyone. So if on a body there are at different points there are different loads. Okay, if on a body there at different points there are different loads, then you can find the stress in each individual section, and you can also find the elongation of each section individually. Is it fine to you guys? Please answer me, the live students. Did you understand it or not? Please give me a yes or no. Yeah. Okay, so we are going to try one question on it. Just a moment. Okay, so let's try one problem. Okay, let's try this one. Let's try this problem, guys. I'm very sure we can do. See, if you're not able to see the image, I'll just give you something. All the live students must try. Just a moment. So I think this is not very clearly visible. So I'll just give you one more way. A good image, huh? Yeah. Now I think it works. Okay, come. So you please try this question. I think that this is now perfectly visible to you guys. So please try it. The live students, you guys can please try. Please try the question. Yeah. Please try, Pavitra. Please try this question. Yes, you please try. I'm waiting for your answer to come. A very simple question. Please try it. All the live students, you must try the question. Please try. Let's see how we can do. And all the new students, please don't forget to subscribe the channel also. Please do subscribe. Please try to do. Now in this question, what is going to happen? See, again in this question we can see that on the body we are having loads at multiple points, right? On this body we are having the loads at the multiple points. So this is 100 Newton, okay? This is 500, mm, and this is what? This is 250 Newton. This is 250 Newton, okay? This is 200 Newton. This is 200 Newton and this is 50 Newton. This is 50 Newton, right? And we are having this is 400 mm and this is 1700 mm. Okay. Now in this case you can clearly see that there are different loads. Okay. In this case you can clearly see that there are different loads at different points within this body. Now, when there are different loads, at different points within this body, and what is the name of these points? So it is K, L, M, and N. Right? Now, when there are different loads at different points on the body, this obviously comes under the bars in series concept. Right? Now see what we have to do, sir. So the first thing that we must find the reaction. But sir, if you see all these load together, the net loading is 0. So net loading is 0, so that means there is no scope of, there is no scope of what? There is no scope of reaction, right? And also there is, it is not fixed from any side. So there is no reaction in this case. Now when there is no reaction, you don't have to find the reaction, and what you have to do then? You have to find the axial load. You have to then find the loading diagram. So now let's make the loading diagram. So I'll see this is as positive and this is going to be the negative. Okay. Now this 100, this is positive. So I'll go like this. Right. Now till the application of next load will move by the straight line. Okay. Now this direction, when I see, this is negative direction. See, this direction was positive. I go up by 100. Now when I see this direction is negative direction. So plus 100 minus 250, that is minus 150. Now till the application of next load, we go by the straight line. Now this direction is positive. So minus 150 plus 200 minus 150 plus 200, this will become plus 50. Now till the application of next load, we move by the straight line, and this is plus 50 and this is direction, this is minus 50. So plus 50 minus 50 will become what? It will become 0. So this is going to be your loading diagram, right? Please answer me, guys. Very simple. Right? There cannot be anything simpler than this, isn't it? Whenever we are seeing a load, we have to move as per the direction of the load. And wherever I find a new load, I just have to include it. Right? Easy, no? Please answer me. Right, I hope it is easy to everyone. You find it. Everyone is comfortable with it. Right. Now wonderful. Now once the loading diagram is made, and now you can see also that this loading diagram is becoming 0 at the very end. So any loading diagram, any loading diagram when becomes 0, at the end, that means you have done everything correctly. Okay. Now, once you have the loading diagram, now what you know? So you know the load on each section. So P in KL, the load in KL, it will become 100 Newton. Okay, the load in LM, it is going to become minus 150 Newton, right? And load in MN, it is going to become plus 50 Newton. It is going to become plus 50 Newton. So once the loading diagram you have the loads in every part. Okay, you have the load in every part. Okay, you have the load in every part. Now please see. If we talk about the stress on each of the parts, see, effortless thing, effortless, isn't it? So in this question, what it says the total change in length. So you need to get the net elongation. So it will be the elongation in KL part. It will be equal to the plus LM part plus MN part. Okay, elongation of KL plus LM plus MN. Okay. Now what is going to be the net elongation then? So the net elongation is going to be, so in KL part it is 100 into L. What is the L for this part? This is 500 upon area. Area is given in the question, it is 25. And Young's modulus is also given. Young's modulus is 200 GPS. So you convert it into megapascal. Okay. So this will be same for everything now, because every time we are using the same formula, PL upon A. So since area and Young's modulus are same only, you are going to get the same thing. So now what is delta LM? So delta LM will be minus 150. Okay, and what is the length of LM? So this is 1700 minus 900, that is 800, plus delta MN, it is going to be 50, and this is going to be equal to into 400, right, into 400. So from here we are going to get the net elongation as, we are going to get the net elongation as, so see what we are going, so this is 100, so I'll just cancel the 0 out, so it will become 500 minus, so it will ultimately become minus of 0.01 mm, right, because we are taking it in mm, right. So what are we getting ultimately? We are getting minus of 0.01 mm. So it will become how much then? So it will become how much then? So in micron meter, it will become, so it is in mm. Now to convert it into micron meter, we need to multiply it with 1000. So this will become minus of 10 micrometer. 10 micron meter. I hope it is fine to everyone. Please give me a yes or no if it is clear to you guys. Yeah. Please answer me. Please tell me if it is clear to everyone or not. Is it? Yeah. Now let's try one more question. Come, we'll be trying a few more. Yeah, now let's try this one. Come, let's see how we can do it. So the live students, please attempt this question. I hope from the first question the concept is clear to you. Please try to do. See, in the same approach, you can solve this question. So you are asking, sir, in the last question, how the loading diagram becomes zero. So see how it becomes zero. So see, we just follow the flow of the loads. Okay, we started from the leftmost point and we move towards the right. Okay, now at K, now at K, what is the now at K? See what is happening at K. So we are having a load and we are using this sign convention. Okay, so this is 100 kilonewton load and this direction is a positive direction. So I'll pick I'll go, so this is your baseline, above it that it's positive, below it is negative. So what we have done, so we have moved 100 in the positive direction. Okay, so we reached this point. Now till the application of next load, we'll move by the straight line, right? And we reaches this point. Now at this point we are having we are having a load of 250, and see this direction is a negative direction. So this is a negative direction. So we'll go when we this is plus 100 plus 100 in this direction is minus. So plus 100 minus 250 it will become minus 150. Now till the application of next load we move by the straight line, and minus 150 this is plus 200, so minus 150 plus 200 that is plus 50. So we reach till this point. Now till the application of the next load we are moving by the straight line, and now when I see this load I just include it. So this will become plus 50 and this is minus 50. So plus 50 minus 50 will become 0, right? And afterwards, see, once the loading diagram is made, you now know that what is the uh, load in each of the individual section. Okay, and once you know the load in each of the individual section, what you can do, so when we know the load in each of the individual section, we can find the elongation or the deformation, or you say the stresses in each of the individual section. Now for deformation, we can simply add those, so we get this answer. Now you please try this question. I'm very sure we can do it. The live students. Yeah, sure. No problem. You please try this question. I'm waiting only. Is it done? Is it done? Please try to do this question. Okay, okay, I'll wait. I'll wait. You please try it. No worries. So what are we getting? Yeah, right, very good. So this is your D option, right? So again, see how we can do it. So see right away when you see this question, you understand that this is the question of the bars in series. So what we have to do, so we have to make a loading diagram. So this is 200 in this direction. So when I see this direction, I go in the positive. Now till the application of next load, I can go by the straight line. Now this direction, this is the negative direction. So plus 200 minus 400, it will become minus 200. Now till the application of next load, we can go by the straight line. And minus 200, this direction is plus, so minus 200 plus 300, that will become plus 100. Now till the application of next load, we are going to have the straight line, right? Okay, and this will become plus 100 minus 100, it is going to become 0. Now once the loading diagram is made, that means what happened? Once the loading diagram is made, so what happened? So loading diagram is made, that means what? So loading diagram is made, that means that now you have information about the load in each of the particular section, right? So for example, in PQ section, the load is 200. Okay, in PQ section we got the load now, that is 200 Newton, right? In QR section the load is minus 200 Newton. Okay, and in RS section the load is plus 100 Newton. The load is plus 100 Newton. Right, the load is plus 100 Newton. Right, so this is the condition. Okay, now what we can do, so we have to find the net elongation. So it is going to become, the net elongation, it is going to become how much? So it will be the elongation of each of the individual sections. So in the first section, it is going to be 200 into L, that is 500 upon area. Area is 10 into Young's modulus. Young's modulus is 200 GPa. So 200 into 10 to the power 3 minus, in this section, it is going to be minus 200. Okay, into L. L is 1000 upon 10 into E. E is 100 into 10 to the power 3 plus 100 into 500 upon area, that is 10 into E. E is 200, so it is actually 200. This is also 200 into 10 to the power 3. Now you can simply add them, right? So see how much it will become. It will become, so see, we have put all the values in mm, right? So this is going to become 200 and this is going to become point 0.05, right? Isn't it? 200 are gone, so it is 0.05 minus, so it is going to be zero point 0.1, right? Minus zero point 0.1 plus this is going to be 2.5. So 4 and this is 4, so it will become, so see, it will become 0.0, see, 200, this will become 2, this will become 2, so 1 by 20, right? So sorry, 5 by 20, that is 1 by 4. Okay, so 1 by 4, it will become 0.25, right? Right, so 100, this is 2, this is 2, so 5 by, sorry, just a moment, it is coming out to be 5 by 40, right? 5 by 40, so 1 by 8. Understood? So now when you are solving it, what you are getting? You are getting 0.25, right? So this is minus of 0.25, isn't it? Minus of 0.25, okay? Okay, mm. Okay, so minus of 0.25, that means we are getting, so it is minus of 0.025, so that means we are getting minus 25 micron meter. So what is the answer? D is your correct answer. I hope it is fine to everyone. Right, so see, one way you can do through the FBD, that is the free body diagram. Another way which I prefer is the loading diagram way. Because in this case, if at all you have made any mistake or you have missed something, then also you can basically deal with the question. Right? Now let's do one more question. So the live student can respond to me if you are able to get this concept or not. And all the new students, I request you to please like and subscribe the channel. Alright? Now in this, what is given? Area is given as 700 mm square. Area is 700 mm square and we need to find stress in QR. Okay, I'll just write it here. So the area is 700 mm square and the stress in the QR section that we need to find. Please go for it. I'm very sure we can do. Please try to do. Yes, yes, waiting only, my dear, waiting. Please try to do. The live students, I am expecting you to answer. Please do it. Please do it. Please do it. Very good, Kirti. Okay, I'll do. Preta, have you done it, beta? Have you also done it? Okay, I'll do. Now see how we can try this question. So see again in this question right away when we see this question we can say that this question belongs to the bars and series part of the physics. Now see in this you need not to find the reaction. Why sir? Because see all of these forces when you see them together you are going to find it that they are balanced only. Okay. Now see when you see this direction you take it as positive so it will go like 63. Now till the application of next load you can go by the straight line and 63 this direction is negative direction so 63 minus 35 so it is going to become how much so it will be 28 isn't it 63 minus 35 so this is going to become 28 right okay 63 minus 35 63 minus 35 right now till the application of next load we can go by the straight line. Now this is the minus direction so 28 minus 49 28 minus 49 this will become minus 21 right 28 minus 49 so minus 21 now till the application of next load now this is the positive so this is minus 21 that will become 0 so the loading diagram becomes 0 in the end that is the indication that you are doing everything in the right manner in the right way okay now see they are asking you the stress in the QR section. Now when I see the stress in the QR section I can see what in the QR section the load is 28 kilonewton that is 28 into 10 to the power 3 upon area is 700 so from here what are we getting we are getting see 40 megapascal isn't it 40 megapascal so what is going to be the option the A is the right option right understood very easy isn't it now let's try one more question. This is a good question. Let's try this one. Okay, let's now try this question. I'm very sure we can do. Please try to do this one. So the live students, if you haven't subscribed the channel yet, please do subscribe also. That is our humble request to you guys. Okay, now let's try. Kirti, Pradipta, you need to solve this. So all of you are understanding this or not? Are we understanding the concept? Okay, Pradipta. You are saying you need some more time to solve the question. So see, I tried to wait as much as possible. Okay, so you please try this question as well. I'll be waiting. Kirti, you please also try to answer this question. See, this is a load P here, a load F here. Here E is the Young's modulus. This section 3 is the Young's modulus. Please try this one. I'm quite sure we can do it. Please try. Please do. Please try to solve it. So, Pradipta, you are answering 3. So you are very near. I think you are making a little mistake. Some mistake is happening. Otherwise, You are very close to the solution. Please do. Please do. What about you, Kirti? You can also please try the question. Please go for it. I'm very sure we can do. Please try solving this one. I'm very sure we can do if we try to. Very nice question it is. Please try it. Any answers? Okay, so I'll do. So now what it says that there is an horizontal bar with a constant cross section is subjected to loading as shown in the figure. So we are having something like this, right? We are having something like this. Okay, and this is P and this is F. This is P and this is F, and this is 3 times E, and this is E. Right now, see, if this is P, this is F, so let me suppose that we are having the reaction that is F minus P. So how F minus P? Now see, when I assume this direction of the reaction, obviously I have assumed that F is greater than P. Okay, because see, the direction of the reaction is always opposite to the net external force on the body, right? Right, so if I'm making this direction of the reaction, so I am obviously assuming that the force F is greater than the force P. Then only the resultant external force or the net external force on this body will be in this direction, and hence you are assuming the reaction to be in opposite direction. So this will be F minus P, like this. Okay, now see what's going to happen. So we are having to make the loading diagram. So this is F minus P. So this is F minus P in the positive direction. Now till the application of next load will go by the straight line. Now this direction, when I see, this is a positive direction, so f minus p plus p, it will become f. Now till the application of next load, we can go with the straight line, and now plus f minus f becomes 0. Plus f minus f becomes 0, right? Okay, so once the plus f minus f becomes 0, okay, that means the loading diagram is correctly made. Okay, now they are saying that for elongation of C to be 0. Now what is the elongation of C here? So it is nothing but your net elongation, and it is the elongation of the AB part plus elongation of the BC part. Okay, now what is going to be the elongation of the AB part? It is going to be f minus p, and length I believe is given as L only. This is also L, this is also L. So it is going to be f minus p into L upon A, and the Young's modulus is 3. So it will become f minus p L upon A into 3e, and this is f plus f, this is L upon A is equal to 0. Right, so what it will become? It will become f by 3 minus p by 3 plus f is equal to 0. So this will become 4f, this will become 4f is equal to p. So what they are asking you? They are asking you the ratio of p by f. So it is going to become 4. So the answer to this question is what? Answer to this question is 4. I hope this is fine to everyone. Right guys? Yes or no? Please tell me yes or no, all of you. Yeah? So now let's try one more. Okay, let's try this one. I'm very sure we can do. Please go for it. Please go for it. I hope the concept is getting clear to you. Let's see how we can do. Please solve the question. I'm waiting for you guys to solve. Are you trying it? Yeah, please try. See, in the same way we can do this question. How can we do this? Are we trying? Are we trying or not? Please try to do. How can we try this question? So see, when you see this kind of a question, when cross section is variable, this is variable. So there, what you can do, you can always use the concept of bars and series. See how we can try this question. Now see, this is 100 mm, this is 100 sir, but this is not on the axis. So see, if you bring them to the axis, it will become, so see, I'll just tell you something. So this 100 is here. Let's talk about this 100 kilonewton. Okay, and this is the, if you know to play with the forces now, definitely things are going to be very easy. Now to this 100, what we can do, we can make 100 kilonewton here, and you can make 100 kilonewton at here, right? 100 and 100, right? Now if you see these two 100 together, two equal and opposite forces are causing what? They are causing couple, and this is causing the couple. Let's suppose this is the distance is x. So this is 100 into x, isn't it? And the nature of this movement is counterclockwise, right? Now we have one more. This 100 is also there. And from the symmetry I can see, and from the symmetry we can clearly see, and from the symmetry, we can clearly see that this 100 is also at the same distance from here, right? This is x, so this is going to be 100 and this is going to be 100. Okay, so 100 will become 200. Now you see this 100 and this 100, they are creating a couple that is clockwise, that is 100 into x. Now two equal and opposite couple on a body, definitely they are going to cancel each other's effect. So this 100 and this 100 will become 200 at the center. Okay, okay, so see, this is going to be very simple. Okay, now I can reframe this question or rephrase this question. Okay, so this is this only now. See, see, this is how much. This is 200 kilonewton. Okay, this is how much. This is 50 kilonewton. 200 kilonewton, 50 kilonewton, and this is going to be. So they are asking you the tensile stress, the maximum stress in this body. So what do you have to do? You can find the reaction. So if this is 200, this is 50, so obviously this is 250. Now we'll make a line like this. Now this side I'll assume positive, this side I'll assume negative. Okay. So see, this is 250. So if you are having any problem, you can think of it as a horizontal problem. Don't get confused. Okay, you just convert this problem or think this as a horizontal one. So once you picturize this problem in a horizontal problem, what you are going to see, you are going to see that you are having ease in solving. So this 250 is positive then, so it is going to be 250. Now till the application of next load, we can go by the straight line. Okay, we can go by the straight line. Okay, now this is what we are seeing, that is 200. So 250 in this direction is negative, so 250 minus 200, this will be plus 50 till the application of the next load, and this plus 50 minus 50 will become 0. Okay, so this is the loading diagram. Now talking about the stress. So what is the stress? So let's suppose this is the part. So in section 1.1, that is in the AB part, if we say, so the load is 250 kilonewton, that is 250 into 10 to the power 3 upon area. So it is having a square cross section. So square cross section, that means 100 cross 100. Right? So this will become 25 megapascal. Right? And in the 2 part, this is going to be 50 kilonewtons. So 50 into 10 to the power 3 divided by, so 50 is square of 50, that is 50 cross 50. So this is going to become 20 megapascal. So what is the maximum stress? It is C option, that is 25. I hope it is fine to everyone. Okay, now let's try one more. See, a very simple question. Come on, I hope you can do this now. Come on. So in this, you need to find the deflection at point A. Please go for it. I'm very sure we can do it. So in the last session, we have spoken about the tapered bar as well. Now you have to do that. Please go ahead. Shweta, were you able to do the last question? Please tell me. Have you solved the last question? Okay, so you couldn't do, but okay, so you're saying, sir, you couldn't solve it because you needed a little more time. Okay, that's fine. But when you approached the question, you were approaching the right way, isn't it? Were you approaching the right way or not? Okay, so you were approaching the right way only. So that means you are getting the concept, right? Okay, I'll give you some time in this question. Don't worry. Okay, so you please solve this question. I'll just get some water for me as well. Huh? Is it done? Please tell me. Is it done, guys? Okay, okay. I'm waiting. No worries. Okay, so how can we do it? Okay, now I'll do. So now in this case, what we can see that we are having so only one load is there, so we can have the reaction that is 30 pi. Now if I draw the loading diagram, it is going to be 30 pi, right? And till the application, so the load is 30 pi only. Now see what you have to do. So see, in this question, we are having some uniform cross section bar and it is attached with a tapered bar. Okay, so what we can do, so what will be the net elongation here? The net elongation is going to be, in this case, the elongation of the tapered bar plus the elongation of the bar having the uniform cross section, that is the prismatic bar. Okay, so for tapered bar, it will become PL upon A, so that is 30 pi, and this is kilonewton. So now we know that formula of the tapered bar is, so 30 pi into 2000 to kilonewton, so we can have 10 to the power 3. Okay, and what is the length? So it is 2000. So I'll write on the next slide so that you can see. So see, very simple. In this, we have to just combine the elongation of the tapered bar and the prismatic bar. So for tapered bar, it is going to be 30 pi kilonewtons, so 30 pi into 10 to the power 3 into L, so L is 2 meter, that is 2000, right? Divided by pi by 4, 20, and so see the larger diameter into the smaller diameter, 20 into 10, 20 into 10, right? Okay, and this is going to be 20 into 10, and this is going to be E. So E is how much? It is 2 into 10 to the power 5, right? Now we'll be having, you see, in the second section, the load again is 30 pi, okay, into 30 pi into, we will be having for the prismatic bar, the length, so it is 10 to the power 3, and the length is what? It is 1.5 meters, that is 1500, divided by area, that is pi by 4 into 10 square into E, that is 2 into 10 to the power 5, right? Right, so now from here we can find the net elongation, right? So what is it? So what is it going to be when we try to find it? Please answer it, guys. So what are we getting from here when we calculate? So when you are going to calculate it, you are going to get 15 mm. Okay, what you will be getting? You will be getting 15 mm, right? Okay. So guys, like these problems can come like this, and you can now understand. I hope you have understood the whole thing. Okay. Now let's move to one more problem. So let's suppose there is a wire. Okay, there is a wire, and this is your steel. Okay, and we'll be having this as 6 kg. And this is going to be C for steel, and this is going to be let's suppose it is copper. So first part is steel and the second part is copper. Okay, and there is a load here also. Let's suppose there is a mass here, so we are having this as 6 kg, we are having it as 2 kg, right? This is your copper, and what is the information given? So we are having this as see, this is going to be, let's suppose this is 2 meter and this is 1 meter. Okay, and you can neglect the length of this weight, just consider the masses. Please go for it. I'm very sure we can do. Please go for it. And let's suppose Young's modulus of steel is 2 into 10 to the power 11 Newton per meter square, and that for the copper, and that for the copper it is 10 to the power 11 Newton per meter square. Please try it. I'm very sure we can do. Please go ahead. Please go ahead. What you need to find? You need to find the net elongation here. Okay, the net elongation. Please go ahead. I'm very sure we can do. Please do it. Very, very simple. Please try to solve. I'm very sure we can do. Please try it. So see how we can try to do it, how we can do it. So the first thing is that you need to find the reaction. So what is going to be the reaction? This is 6 kg, this is 2 kg. So the reaction will become 8 kg. Okay. Now if I draw the loading diagram, it will be like this. So 8 kg is there. Okay, so 8. Now till the application of next load, we can go by the straight line. Now 8 and this is 6 kg. So 6, this is always acting downward. And this will also act downward. So 8 minus 6, that will become 2. 8 minus 6, that is going to become 2. Now till the application of next load, we can go by the straight line. And 2, and this is the downward force. So 2 minus 2 will become 0. Right? 2 minus 2 will become 0. So now what will be the net elongation? So can I say the net elongation is going to be the elongation of the steel plus the elongation of the copper, plus the elongation of the copper, right? Okay, elongation of the copper. So for steel, what is going to be? So in this, we are having this 8. So can we write 8G? What is L? L is 2 meters, so 2000. Or just write 2. See, because G normally we put as 10, no? Okay. Or 9.81, the unit to it is meter per second square. So we'll write 8G into 2 upon, so this will be PL upon AE. So what is the area? Okay. What is the area? So area is given, area is given actually. Okay, area is not given, let's suppose. So both the area, let's assume to be same. Actually, area also given. I missed it. So I'll write like A. No worries. Okay. Area is there and Young's modulus is 2 into 10 to the power 11. Right? Plus, what is for the copper? So it is going to be 2G. What is the length? The length is 1 meter upon area, and this is 10 to the power 11. So this will become how much? So 8G, so this will become 16. And so if I take A into 10 to the power 11 as the LCM, it will be 16G plus 2 and 4. So it will become 20G upon A into 10 to the power 11. 20G upon A into 10 to the power 11. This is going to be your net elongation in this case. Understood, guys? Yes or no? Right? Is it clear? Please answer me. 20G upon A into 10 to the power 11. Right? I hope this is fine to everyone. Right? Okay. So very simply again using the same concept we have done the question. Okay. Okay. So I hope this particular thing is clear to everyone. Right. Now let's move to the next part. So there can be one more case in this scenario. So if you see, like let's suppose we are having a question like this. Now if I say this is P, if I say this is P and this is let's suppose L by 3 and this is let's suppose 2L by 3, 2L by 3, and now see you will be able to solve this question very easily. If you have to find the elongation of this whole bar, if you need to find the stress in the whole bar, definitely you will be able to do. Now if you see, it is like this, it is like this. So now if you see guys, like what is the difference of this from the previous one? So it is having the other end also fixed. Okay. Now we can try to find the reaction first. Once the reaction is found, you can clearly solve this question. Okay. Now please try it. Please do guys. So see how we can do this question. So see in this question, see reactions are not there. In the previous question, either the reactions were given or you can calculate or you could calculate the reactions very easily. But in this case, you cannot do like that. So see what is going to happen. Now we are going to assume some reactions. Okay. So let me assume that reaction at A and C is Ra and Rc. Okay, now what we can say, see when you are assuming the reaction, so see first step in this kind of a question of it is, see you can assume both the reaction in the same direction initially. See when you are assuming both the reaction in the same direction, in the same direction initially, you can right away write what you can do. So you can right away write that the sum of reaction, that is Ra plus Rc, it is going to be equal to the net load. So Ra plus Rc will become equal to P. Okay. Okay. Now since it is fixed at both the ends, the net elongation of it is going to be 0. The net elongation of this is going to be 0. Okay. Now when the net elongation is going to become 0, see we can write the elongation. So for that, again I will start from the left hand side and it will be Ra. See how I am writing it, please observe. So this is positive sign, so it will be plus Ra into the length, that is L by 3, upon area into Young's modulus. Now we reach this B point, so this is going to be Ra, this is minus direction, so Ra minus P into length, that is 2L by 3, okay, upon A into E, and we reach the C. So when you reach the last point, it will become 0. See, very simply, so I started with the Ra. So see, as I was saying in the last session also, we have only one formula, that is PL upon A. For deflection, we have only one formula, that is the PL upon A. Okay, so see how we did it. So we started we started from the leftmost point, and we are moving towards the right. Okay, so we start writing the load from A, so this direction is positive, so we write plus RA into the length till the next load. So till the next load the length is L by 3. Okay, till the next load the length is L by 3. Then at B we are having another load, so we are including the another load just like in the loading diagram we did, and afterwards we are having the length, that is 12 by 3 upon A, and combinedly it will become 0. Okay, okay, so now this is going to become RA plus 2 times RA minus 2 times P is equal to 0. So from here RA will become 2 by 3 of P. Okay, and RC will become P minus 2 by 3 of P, so it will become P by 3. Okay, understood? Yeah. Okay, so once the reaction is fine, when the reaction is found, okay, so once the reaction is found, okay, once the reaction is found, this problem has no difference. This will have no difference from the previous problems we have seen, isn't it? Right? So we can, after this, we can make the loading diagram, we can find the stresses in each of the section and everything that is asked in the question, or that could be asked in the question. So I hope this is also clear to everyone, right? Now see, we have one more case. So see, we have when two bars, let's suppose steel and copper, they are connected one after the other. Okay, that is what we call as the bars in series. Now if we say are bars in parallel. Now, what is the meaning of this thing? So, bars in parallel, okay, or we could say bars in parallel, or we could say composite bar. Bars in parallel, or we can say composite bar. Okay. Now, see what is happening in bars in parallel or composite bars. So, let's suppose we are having two things. One is steel and one is copper. Okay. Now, if we are attaching them one after the other like this, okay, steel and the copper. Okay, so now see, if there are two different materials and they are joined like this, like a sandwich, one over the other, then we will call this arrangement as the parallel arrangement. What we are going to call this arrangement? We are going to call this arrangement as the what? As the parallel arrangement. So this is going to be your parallel arrangement. Now, if I put some force on it, if we apply some force on it, so see what is going to be the situation in this case. So see, this load is going to be distributed or is going to be carried by both of these bars. So this P will become P of steel plus P of copper, right? So this load, part of this load will be borne by the steel and the part of it will be carried by the copper. Okay, so this is the one equation. The other equation is that, so in the case of composite bar, remember, they must always maintain, they must always maintain, they must always maintain their contact. Okay, they will, or they must always be together. Now, for these two be together, the elongation or the deflection of both of it must be the same, isn't it? It must be the same. So can we write like this? So delta is steel plus delta is equal to delta copper. See, they will be only be able to maintain their composite form or their togetherness or their whatever you say. Okay, their composite structure. Okay, their elongation has to be the same. If the elongation is not same, they cannot maintain themselves together. Okay. Okay, so in this case, see, in the case of composites or in the case of bars in parallel, what is going to happen? The elongation of each of the bar will be same. Understood? The load will be distributed amongst the individual constituents and the elongation will remain the same. I hope it is fine to everyone. Okay? Then, wonderful. So let's see one question. Just a moment. Okay, so let's try this one. Let's see how we can do it. Please go for it. So, Prita, you are saying, is it series or parallel? So, my dear, if the individual, so if these, there are three wires here, if they are, placed one after the other, they will be in series. And if they are placed like this, right, they placed like this will be your parallel. This will be your parallel arrangement, right? Because see, in this case, the load is acting on the very center. So when the load is acting on the center, the strains of each of the bar is going to be the same. Strain of each of the bar is obviously going to be the same. Now, when strains of individual, individual constituents or individual parts of the arrangement is same, then we call it bars in parallel, right? Okay. Now, please try to solve this question. I'm very sure we can do. Please try to do. So, all the students who haven't subscribed the channel, please do subscribe. Please try. I'm waiting. I'm waiting. So what is the answer to this question? How can we do it? Please try doing it, guys. So see how we can do it. So it says a rigid bar is suspended by three rods made up of the same material as shown in the figure. The area and length of the central rod are 3A and L respectively, while the other two rods are 2A and 2L respectively. If the downward force of 50 kN is applied at the bar, the forces in the central and each of the bar. So let's suppose this is 1, this is 1, this is 2, and this is 3. So can we say that, so let's call it P1. So P1 plus P2 plus P3, right? It is 50 kilonewton. Let's suppose P1 plus P2 plus P3 is how much, sir? It is 50 kilonewton. Okay. Now P1 plus P2 plus P3 is 50 kilonewton, and also see, since the load is applied on the center, we can say that the elongation of each of it will be same. So can we write delta 1 is equal to delta 2 is equal to delta 3. Okay. Now what is the delta 1? So it is P1, the length of the outer rods are 2L, okay, upon 2A into E is equal to delta 2. Delta 2 is P2 into L upon 3A into E, and this is going to be P3 into 2L upon 2A into E upon 2A into E. So now from here what we can do, so can we write, so can we cancel out this LAE, LAE and LAE? So can we write P1 is equal to P2 by 3 is equal to P3. Okay, so P1 and P3 are the same, and this is equal to P2 by 3, right? So now we can write it here. So can we write P1 plus P2 by 3? So P2 will become 3 times P1 plus P3 will become, so P3 and P1 are the same only. So can we write P1, and this is equal to 50 kilonewton. Okay. Okay, so from here can we write that P1 is coming out to be 10 kilonewton, and since P1 and P3 are the same, so this is P3 also, this is P3 also, and what is going to be the P2? So P2 is going to be then 3 times P1, that is 30 kilonewton. I hope it is fine to everyone, right? Yeah. Is it clear to everyone? Please answer me. Right? Bole. Any issue in this? Please answer me. Please answer me. Is it fine to you? Yes or no? I hope this is clear to everyone. Wonderful. Okay. So guys, this is also a kind of, bars in parallel only, right? So now we have seen a lot of things there, and so okay, we can try this one. Okay, I think this much is sufficient, no? So you have understood this concept. Now let's move to a very, very important thing, that is the temperature stresses or the thermal stresses. Okay, that is the thermal stresses. So why we are naming it the thermal stresses? What could be the possible reason? So sir, obviously when we are naming it thermal stresses, so definitely it has something to do with the temperature, right? When we are naming it the thermal stresses, so definitely it has something to do with the temperatures, right? Yes or no? Yes, sir, definitely. That's why the name is thermal. Okay, so something related with the temperature, we are normally naming it as the thermal thing. So now see, in this particular part of the physics, we are interested in dealing that when a body is subjected to a change of temperature, how it behaves, what are the stresses generated into it, whether they are generated or not generated, right? Okay. So just a moment, guys. Huh? Please do it. So now see, just so now see, we will be talking about the thermal stresses. So see, let's suppose we are having a body. Let's suppose we are having a body like this. Okay. Let us suppose that we are having a body like this somewhat. Okay. Now this is L. This is B. And let's suppose this is D. Okay. Now I want to ask you this. See, if the temperature of this body, if the temperature of this body is increasing, okay, what is going to happen to this body? So normally any material do what? So any material has show the tendency, any material show the tendency of elongation, okay, when subjected to, or tendency of expansion when subjected to an increase of temperature, when subjected to an increase of temperature. Yeah, sorry, just a small technical issue. So now when I increase the temperature of this body, what is going to happen? This is going to have a expansion in all the directions, right? That means that every dimension of this is going to increase. Every dimension of it is going to increase. The L will become L plus delta L. Okay, L plus delta L. This B will become B plus delta B. Okay, and D is going to become D plus delta D. This is going to become D plus delta D, right? D plus delta D. Okay, so basically it is going to become like this, right? Some increase in the dimension is going to happen. Now see, you also might be able to understand this, or you also believe this, that a different material behaves differently when subjected to the same change of temperature, isn't it? Yeah. Do aluminium, steel, copper, and any other material, for instance, are they behaving the same way? Are they behaving the same way when subjected to a particular change of temperature? No, sir. Aluminium will show some different tendency, steel will show some different tendency, right? And other material will show some different properties. So, which is the material property that governs the thermal behavior or the behavior of any material subjected to change of temperature? This is given by, this is the material property, that is alpha, and this is what we call as the coefficient of thermal expansion. Coefficient of thermal expansion. So this is one physical property that governs basically that when subjected to a change of temperature, what will be the change of dimension of any particular material, right? Okay, so see how it is going to be. So see, for example, this body, this is subjected to a change of temperature. Now, when this is subjected to a change of temperatures, the length will change due to this temperature change, and that will be alpha delta T into L, right? The change of width due to temperature, that is going to be alpha delta T into B, and the change in D thermal, that is going to be alpha delta T into D. Okay, so see, very simply, what we have to do, see, very simple expression. See, whenever a body is there, what is the change in dimension, you can easily calculate through this equation. Please do it. Okay, so very easy. Okay, the change of any dimension due to this temperature change, you can easily calculate using this expression. And from here, if you see what is the dimension or what is the unit of this alpha, so the unit of change of length is meter. This is length, that is meter. So meter will be cancelled out, and change, what is the unit of the change of temperature? It is going to be 1 upon degree Celsius or Kelvin. So this is the unit of alpha, right? Now, a very important thing. So see, one kind of a question that can be asked to you, that see, you will be given some dimension and you will be given some alpha, okay, and it may be asked to you that this much temperature is change or this much temperature is increase. What is going to be the change in that particular dimension, be it length, width, or depth? Okay, be it anything, right? So alpha is going to be, the unit of alpha will be 1 per degree Celsius, right? Now see what is going to happen. Now we had this body. Let me take a picture of it. Okay, I'll just make it again. Yeah. So we are having this body. Let's suppose we are having this body like this. This is L. This is B, and this is D. Right? This is D. So now when the temperature of this body is increased, when the temperature of this body is increased, when the temperature of this body is increased, so when the temperature of this body is increased, what is going to happen? When the temperature of this body is increased, what is going to happen? it is going to increase in all the dimensions. It is going to increase in all the dimensions. Now the question is that what will be the temperature stress or what will be the thermal stress in this body? Thermal stress in this body. Okay. Now before you answer it, I want to give you one example. So just see it. Okay. So see my hand. Okay, this is my hand. Now please observe one thing. So this is first situation. I am having this hand and I want to do like this with my hand. I want to do like this with my hand. I want to do like this with my hand. Whatever I want to do, I am doing with my hand. Okay. Now this is the first situation. Now you please realize this. Okay. Now the next situation or the other situation can be, so see, I want to do like this. I want to do like this, but someone is stopping it. Someone is stopping it. Okay. Now when I want to do like this, but someone is stopping it, the first situation in which I can do whatever I want with my hands. And the second situation is that someone is stopping me from doing what I want to do with my hands. Right? Now condition 1 and condition 2, in which condition my hands are going to realize some stress in them. Right? What is your answer to it? The live student can respond to me. In the first situation, I am doing whatever I want to do with my hands. But in the second situation, what is happening? Somebody is stopping me to do what I want from my hands. Right? Now, you definitely would say, so it seems like that in the second situation will generate some stresses or our hands will feel the stress. See, what I believe, see, God has made everything and nearly He has given the same nature to every material, be it ourselves, be it steel, be it aluminium, be it any material for that matter. Right? So, see what happens whenever, so see what is the situation you wanted to do it and when you were able to do it. When you wanted to do it and you were able to do it, there is no stress in this, right? Why there is no stress? Because there is no restriction. But in the second case, when you wanted to do something and somebody is stopping you, that means that you are having some restriction. Okay. Now, same thing materials also feel, right? When they are free to expand, okay, when they are free to deform due to some physical phenomena, they wanted to deform, they want to deform. So, see, on this body, temperature is increased, it is expanded. It has expanded itself. Now, when it has expanded itself, there is no reason of the stress to come in this particular body. If at all, if it would have been restricted, like the example I have quoted, the same thing happens with us. Na? Sir, we wanted to watch a movie, right? A good movie has just arrived on Netflix, right? But we have to see you, right? Okay, because we are somewhat restricted that we want to crack the NEET for our good career, our good life, right? Now, since we want to crack the NEET examination, we are bound to look at you, and that's why we feel the stress, isn't it? Right? So, whenever what you want, you are being restricted to do that, you will feel some stress on you. Same thing, same way materials also behave. Okay, like for example, in this case, the temperature of this whole body is increased. When the temperature of this body has been increased, okay, it was free to deform. When it was free to deform, it was free to deform. So when it was free to deform, there is no reason of stress to come in this body. No reason for stress to come in this body. So that is why we can say that the stress on this body is zero. The stress on this body is zero. Understood, guys? The stress on this body is zero. Okay. So in this case, there is no thermal stress, and and what we call it? We call it free expansion. This case is what we know as the free expansion. So when a body is heated or its temperature being increased or maybe decreased, and when the body is free to deform, when there is no restriction whatsoever on the deformation of the body, when there is no restriction whatsoever on the deformation of the body, it is going to have no stress generated in the body. I hope it is fine to everyone, right? Right? So see, simply I tell you one thing. When we talk about the normal stresses, okay, in any direction, the stress can come because of two reasons. One reason could be that there is a load in that direction. Other reason could be that the elongation or the deformation is restricted in that direction. Okay. Okay. In any of such case, if any of these two is happening or both of it is happening, then only you will have the stress in some direction. Otherwise, you are not going to have the stress in the direction. Are you getting my point, my dear? Okay. Okay. Otherwise, you are not going to have the stress in that direction. Two things. See, if the load is acting on some direction, there will be stress in that direction. Second thing, if any deformation that naturally happens, it may be due to the temperature, it may be due to the Poisson effect also, right? Okay, then there will be stress in that direction. So just like I'll just quote this. So see, let's suppose we are having a three-dimensional body. We are having a three-dimensional body. Now, when we are having a 3D body, see, let's suppose a load is applied in this direction like this. Okay, so when load is there in this direction, okay, let's call it x direction, and this is y and this is z. So in this case, there will be, if I say like this, okay. Now see, if I so see whatever I am telling you, it is valid only on three mutual perpendicular planes, okay, on which there can be normal stresses. So in this case, there will be some stress in x direction, normal to x direction basically. Why so? Because there is a load in this direction. There will be a strain in x direction, obviously, because something is getting compressed like this, so there will be strain in that direction, right? Now, will there be any strain in y and z direction? Can you tell me? Will there be any strain in y and z direction? So definitely, sir, there will be some strain in y and z direction due to the Poisson effect. Okay, we have seen the Poisson effect. Now, every longitudinal strain is having two lateral strains. So this is coming because of the Poisson's effect. This is coming because of the Poisson's effect, right? Okay. Okay. So see, epsilon y and epsilon z. Okay, they will not be zero. Now, since they will not be zero, there is no reason of the stress to come in y and z direction. Okay, see how I am seeing it. So in y and z direction, can you see any load? No, sir, there is no load in y and z direction, obviously. Now, since there is no load in y and z direction, and r is anything or is there any restriction there in y and z direction? No, sir, there is again no restriction also in y and z direction. So since there is no restriction in y and z direction, there is no load in y and z direction, there is no reason for stress to come in y and z direction. And similarly, like you see in this case, so we are having three directions, that is x, y and z. And when the temperature of this entire body is increased, okay, it is not at all restricted in any direction to deform. So there is no restriction in any direction, there is no load in any direction. So when there is no restriction in any direction, when there is no load in any direction, okay, there is no reason of the stress to come in this body in any direction. So in this case, there is no thermal stress, right? Now see. So let's suppose this is L, okay, and this is your D, okay. Now this is the body, and if I increase the temperature of this body, you tell me, will there be any thermal stress in the body or not? Will there be any thermal stress in this body or not? Please tell me. Please tell me. Will there be any thermal stress in this body? What do you have to say? Will there be any thermal stress in this body? Please answer me. Will there be any thermal stress in this body? Now, many students think this problem in this way. Sir, when the temperature of this body is increasing, we look like it is restricted at one end. So when it is restricted at one end, there will be some reaction and there will be some stress because there is a restriction. So see, you don't have to see like this. Now please understand this. We are talking in any particular direction. So when we talk in any particular direction, see what is going to happen. When you increase the temperature of this body, when you increase the temperature of this body, it is going to deform or it is going to expand somewhat like this, right? It is going to expand somewhat like this. So when it is expanding somewhat like this, so it is having whatever elongation it wanted in x direction. So when it is getting all the elongation that it wanted in one direction only or in x direction only, there is no reason of stress to come. Very good, Kishore. Right? So in this case, there is again no stress. There is no reason of stress in this case. So again, it is a case of free expansion. Again, it is a case of what? It is again a case of free expansion. So this goes again the case of free expansion. Is it fine? Right? Okay, so there is no elongation. Now, if somebody is asking you what will be the change in length due to this change of temperature, so you may say that delta L is alpha delta T into L and delta D is alpha delta T into D. Very simply, you can do. Right? Agreed? Any issue in this? No, sir. Now, please understand this. So, Kishore, welcome to the session. First of all, my name is Dr. Shankar Sir, and I am a physics educator. I'll just give a brief introduction about myself because it seems to me that we are interacting for the very first time. Right. So, this is my credentials. I have done MTech and PhD from IIT Roorkee, and these are some few things about me. Okay. So, because we are interacting, I guess, the very first time. So that is why I am introducing myself. Okay. Now see, let's come back here. So see what we did in this session today. So we are trying to see the first chapter of 11th Physics Part 2. That is the properties of solids. Right? Okay. So in that what we are trying to do, we are trying to realize that how Hooke's law works, how we can find the stress, the strain. Okay. Afterwards, we have seen many cases to tapered bar. We have solved. We have solved the questions in which Young's modulus is varying. Okay, self-weight case. Right. Now we are, and also previous to this, we have done the bars in series. Like if the few bodies are connected one after the other, and some load is applied in between or at the end or within that body, right? Then how to deal with it? We have seen that through one concept of bar connection, that is bars in series. We have seen if two materials are connected one over the other, okay, one over the other, so that forms bars in composite, okay, that we have seen. Now we are seeing about the thermal stresses, okay, okay. Now see, so now what we are going to do, so let's suppose we had this body, it was fixed from one end. So when this body was fixed from one end, when this body was fixed from one end, we see or we have seen there is no stress on this body. But what will happen if I restrict it on the other end also? Okay. Now you first tell me in this case in which direction you are going to have the stress and in which direction you are going to have the strain. Can you please try to tell me that? Yeah. Please try. Can you please try? Please tell me in this case in which direction we will be having some stresses and in which direction we'll be having some strain. Please try to give me that. Anyone? So what is the concept that we have just understood? Now in this case, when the temperature of this assembly or temperature of this thing is going to get increased. So when the temperature is increasing, when temperature the temperature is increasing, so when the temperature of this body is increasing, so definitely it would want to have, definitely it would want to expand in x direction. Yes or no? Will it or is it or isn't it? Yes or no? Right? So it will try to expand in both the direction x and y. Okay. Now when it tries to expand in x direction, is it allowed to expand in x direction? Will it be able to expand in x direction? Hmm? Will it able to expand in x direction? No, sir, because we can see there is restriction in x direction. So what we have learned, so whenever some deformation, some elongation is restricted, you will have some stress in that direction. So x will have the stress because the strain is becoming zero, or the elongation is net elongation is becoming zero, right? The net elongation is becoming zero. I'll write in elongation. Okay. So see, it is not zero because this is becoming zero, right? Naturally, it would want to have some elongation, some deformation in the x direction, but it cannot have the elongation in the x direction. So this becomes zero. So this is there must be some stress in x direction. Now in the y direction, it wants to deform and it has no restriction in the y direction. So it can deform in the y direction, right? So when it can deform in the y direction, is there any reason for stress to come in the y direction? No, sir, absolutely not. There is no reason to have any stress in the y direction. Is it fine? Now, what is our aim to do? So now, sir, we need to find the sigma x. Okay, we need to find the stress in x direction, and that is what we are going to call as the thermal stress. Are you getting my point? That is what we are going to call as the thermal stress. Understood? Okay. So see, when it tries to, so I'll just do, and you'll do your y. Okay. In the delta y you have to give me. Now see, when it is temperature is increased, it is trying to expand. So when it is trying to expand at the supports, there will be some reaction. Okay, please think of it. This body is trying to show some expansion. Now, when this body is trying for some expansion, the load is acting like this. There are wall on both sides. So when it tries to expand, the wall will give some force on it, and which restrict is elongation. So there will be some R is coming. Okay. Now, so this is looking like somewhat the loads that we have been dealing from a long time now, right? This R is quite similar to it. So these are what we call as the mechanical loads. Okay. And in the last session, I told you one concept that you have to use the superposition. What is the superposition? So when on a body, like today also, see we had seen a tapered bar case. I'll just show you. So in the last session also we have done the quite a similar thing. Like for example, we had this case, like this case. So tapered bar we have seen in the last session, right? Now in this case, what we have done? So we had a combination of tapered bar and a uniform bar. What we did, we added their elongations. Okay. Similarly, in the last session, we had the self weight and axial load. When self weight and axial load are both acting on a body, what you do, you combine their effect. You add the elongation due to self weight and you add the elongation due to axial load. When you add both of it, you are going to get the net elongation or the net deformation, right? Right? Now, similarly, the same thing we have to do here as well. What we have to do here as well? So we have to apply the superposition concept. See, what is the superposition concept? Now, see, there are two things. One effect, one elongation would be due to the change of temperature. So we'll call it delta thermal. I'm talking in x direction. Okay, in x direction, right? Whenever you are applying the superposition concept, you always apply in some direction. So here we are applying in the x direction. So when we are applying, guys, in the x direction, so when we are applying in the x direction, so in the x direction there is some delta thermal plus now the effect of this load R. So we will call, so this is what we call as the mechanical load. So in any direction, there will be effect of the thermal, that is the effect of the temperature change, and also the load. So the effect of this load, right? So what is going to be, and net it is becoming 0 in x direction. Net it becoming 0 in x direction, right? Are you getting my point? Now what is going to be the delta thermal? So it is going to be alpha delta T into L, right? Alpha delta T into L. And what is going to be the delta mechanical? It is going to be minus RL upon AE. So this is like a axial load. So due to this load, what is the elongation? The elongation is PL upon A. That is what we are using. But it is compressive. Since it is compressive, we are using this negative sign. So it will become alpha delta TL minus RL upon AE, and this is going to become 0, and this is going to become 0. Now from it, what we are having, so can we write, see, now we are writing like this, alpha delta T into L, alpha delta T into L minus alpha delta T into L minus, now we are having sigma thermal L upon E. So see, R upon A, load upon area. So this becomes some sort of a stress. Now this R, since it comes due to the temperature change, we call it thermal stress. And this is becoming 0. So sigma thermal will become alpha delta T into E. It becomes alpha delta T into E, right? And since you see the load is compressive in nature, so this shall be minus. Understood, guys? Okay, so this is the thermal stress in this particular case, right? Don't see, many students memorize this as a formula. So the formula, when I ask you what is the thermal stress, they say, sir, it is alpha delta T into E. So guys, see, it is not a formula, but it is the stress under this situation. If the situation is changed, the stress may change. That is also we are going to talk about. Okay. But before that, you please tell me that did you understand this concept or not? Yes or no? Did you understand this concept or not? Please answer me. Yes or no, guys? Did you understood this concept? Yeah. And how we have got this formula? Now what you need to do here, so see what you need to do, you need to tell me now that what is this delta y. See, sigma y is 0. Sigma y is what, sir? Sigma y is 0. Now here what you need to do, you need to give me the delta y. Alright? You need to give me the delta y. Okay? So now you need to give me the delta y. alpha delta, let me give you some options, alpha delta t d, let's see if we can do it or not, alpha delta t d 1 plus mu, okay, and we need to have alpha delta t d 1 minus mu, and we are having alpha delta t d mu. Okay, now you please try answering it. I'm very sure we can do. Please go ahead. See, you will be definitely be able to do if you try. Okay, there's no new concept, the same thing that you have to do here. Please try to do it. I'm very sure we can do. Yeah, guys, please try to do. The live student Kunal Pradipta, please try. I'm very sure we can do. So you have to use the same approach. When you use the same approach, you are definitely going to get it. Okay. So see, again you have to do see the same superposition. Okay, superposition is very very useful in this particular part of physics. Okay, right? So see what you can see how you can apply the superposition. So for superposition, for to apply the superposition concept, what you can do, you pick one direction, then you try to put one the effect of, so see this is combination of two things, one is temperature, one is the load. Okay, so when we are having such combination, you break down those things in any given direction and then do the addition. Okay, first you break it, then you join it. Okay, so please do it. I'll just take a 5 minutes break and we'll be back. Yeah, okay, you please try. Please try. I'm very sure we can do. Please do. So see how we can do it. So now in this case, what we have to do again, so sir, we need to see the effects in y direction now. Okay, so there are two things. So when we are seeing in the y direction, let's see in the y direction. So when we are seeing guys in the y direction, there are two things. Okay, this delta y will be due to some temperature, that is thermal. Okay, and some part of this strain will be due to this R, right? So I'll write delta mechanical, right? Delta thermal plus delta mechanical. Okay, now see what is going to happen. So this is going to be delta y. So what is the delta thermal? It is alpha delta T into D. And due to this R, what is going to be the deflection in this direction? Now please see. Let's take it separated. Okay. So we have learned the Poisson effect. Okay. So this is a mechanical load. Now due to this load R, what will be the effect in y direction? So due to, if individually you see this R, if individually you got to see this R, so this is somewhat like this. Okay, so this is your R. Okay, now due to this R, there will be some change in D. There will be some change in the dimension in the y direction. Now what is going to be that change? So we understand that the lateral strain is minus mu times the longitudinal strain. So this will become minus mu times the longitudinal. So longitudinal strain will be sigma thermal upon E. Sigma thermal upon E, and this will become minus mu sigma thermal. What is sigma thermal? Sir, we just have calculated it. It is alpha delta T into E, and this is going to be E, and since it is in the negative because it is compressive now, so it will be minus. So it will become plus mu alpha delta T, and the lateral strain will be delta D upon D. Okay, so this is your mechanical one. So the delta D mechanical will become mu alpha delta T into D. Mu alpha delta T into D. So can we write it here? Mu alpha delta T into D. So from here what we can do, we can take alpha delta T D as constant, and it will become 1 plus mu. So what we'll be having? We'll be having the B option. Okay. So what change will happen in the y direction? What will be the net elongation or the net deformation or the net deflection in the x direction? So definitely it is going to become alpha delta TD 1 plus mu. I hope it is fine to everyone. Okay. So now due to the thermal stress, so this is the thermal stress, remember in this case. Okay. It is, see, thermal stress, there is no formula to thermal stress as such, but you find the thermal stress individually for each and every cases, right? Now see, if I give you one more thing, now you have to try it the same way. So let's suppose we are having a body, and this is fixed from one side, and there is a wall on the other side. Okay, wall on the other side, and let's suppose the gap between it is lambda. Now you need to give me the thermal stress. You need to give me the thermal stress if the temperature of this whole arrangement is increased by delta T. Okay, if the temperature is increased by delta T, what is going to be? What is going to be the stress in this case? Okay, what is going to be the stress in this case? And remember, see, stress only happened when there is a restriction to the elongation. Okay. Please tell me. See, I'm very sure we can do. See, you have to approach the same way and try answering it. So the live students, please let me have the answer. Please try. I'm very, very sure that we can do it. Please try to do. Please try to do. The live students, you can please try to solve this question. Please try to solve this question. I'm quite sure we can do it. Let's try. Let us try dealing with it. Let's try doing it. So see, again you have to follow the same line of procedure. Okay. So see, you can apply the superposition thing if you understood that, right? So see what we can do in this. So if I see now in the x direction again. So first of all, there will be thermal stress in x direction. So why there will be thermal stress in x direction? So there will be thermal stress in x direction, obviously, because see, when you are increasing the temperature, when you are having an increase of the temperature, so when you are having the increase of the temperature, what is happening? What is happening? So when you are having the increase of the temperature, what is happening? This particular body, this particular bar, it will try to have some, elongation or expansion in the length L. Okay. Now, when it is having some expansion in the L, can it have the elongation or the expansion it desires to have, or it may have when there is no wall ahead? So that is not possible. Why so? Because when it is expanding, so when the length is changed by the gamma, it is going to come in contact with this wall, and when it is coming in contact with this wall, it cannot deform any further, it cannot deflect, it cannot elongate, it cannot expand any further. So when it cannot expand any further, it is now restricted, and as soon as restriction happens in any direction, what is going to happen then? So as soon as the restriction happens in any direction, it is going to have the is stress created or stress generated in that. Okay, now see what is going to happen. So there will be some R when it is expanding. When it reaches this lambda mark, there will be some R, there will be some load, okay, and some R will come here. Okay, so what is going to happen now? What is going to happen now? So we are going to see in the x direction. So if I see in the x direction, again there are two things. One is the change due to thermal, that is the temperature, and one is the change due to the mechanical, that is this R. And both when combined is equal to this lambda. Both when combining it becomes the lambda. So what is the delta thermal, sir? It will be alpha delta T into L. This will be your thermal elongation plus delta mechanical. So mechanical will be minus RL upon E. This is the elongation due to this R, and this is going to become equal to lambda. This is going to become equal to what? It is going to become equal to lambda. So now from here, can I write, so sigma R by, can I mark it as sigma thermal? So it will become sigma thermal L upon E, and this is going to become, so I have taken this on the other side, so it will become alpha delta TL minus lambda. So sigma thermal will become alpha delta TL, it will become alpha delta TL minus lambda, alpha delta TL minus lambda into E by L, into this E by L. Do you agree or not? Please answer me. Yeah? Okay. So this is going to be, or this will become your thermal stress in this particular case. Right? This is going to become your thermal stress in this particular case. So as I said, see, thermal stress has no formula. Many people think that alpha delta T E is the thermal stress. No, 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 no. It is the thermal stress in this particular case. Okay, it can be different as the case changes. So like in this case, it is alpha delta TL minus lambda. I hope it is fine to everyone. Now let's see a few questions on this concept. Let us see if we are able to do them or not. Sorry. I'll just give you one question so that we understand the concept in much better way. Right? So we are having, let's just try this question. Okay, let's try this one. Let's see if we can do it or not. Please go for it, guys. Let's see if we can do it or not. Let's try this one. I'm very sure we can do it. Please go for it. Let's try to do it. Please do it, guys. Let's try to do it. I'm very sure we can do it. Please try for it. Please do. So see how it is going to happen. So it says a steel cube with all faces free to deform has Young's modulus is given, Poisson ratio given, the coefficient of thermal expansion is below. The pressure developed within the cube when it is subjected to uniform increase of temperature. So it is going to be, see what? So it says that its all faces are free to deform. So when all faces are free to deform, that means it is the case of free expansion. Now since it is a case of free expansion, you are going to have no stress in this particular thing. Okay. Okay. Now let's see one more. Okay, let's try this one. Please do it. So see, it says a metal bar of length 100 is inserted between two rigid supports and its temperature is increased by 10 degrees Celsius. If the coefficient of thermal expansion is 12 into 10 to the power minus 6 per degree Celsius and Young's modulus, so what will be the stress? So see, what is this case? So it in this case there is a bar and this is said to be inserted between two rigid supports. So what is this two rigid supports, beta? What is this two rigid supports? So basically it is fixed from two ends, right? This is what it means. So it is basically fixed at both the ends. So when it is fixed at both the ends, when it is fixed at both the ends, what is going to happen? So when it is fixed at both the ends, so basically this is the very first case that we have studied, right? Now in this case, what is going to happen? So it says a metal bar of length 100 is inserted between two rigid supports, okay fine, and its temperature is increased by 10 degrees Celsius, so thermal expansion. So in this case, when the temperature of this whole assembly is going to increase, it is the standard case, so the thermal stress will be alpha delta T into E, right? So we'll have two, what is alpha? It is 12 into 10 to the power minus 6. 12 into 10 to the power minus 6. Temperature will be 10 to the power minus 6. Temperature will be delta T, that is T, that is 10, and E is 2 into 10 to the power 5. Okay, and this is going to become how much? So this is going to be 24 megapascal, right? 24 megapascal. Now, if at all in the options minus 24 also would have been mentioned, if then your answer should be minus 24, because you know, like in this case, the thermal stress has to be compressive in nature, right? I hope it is fine to everyone. Okay, now let's try one more. So let's see this one. Okay, let's try. Okay, let's try this. I'm very sure we can do. See, I'm very sure we can do it if we try to. Okay, there is nothing in this question that you don't know or the concept you haven't read. Please do it. Please try to do. I'm very sure we can do. Please try to do it. Very, very simple question. Just in the same line as we just have understood. Please try to solve this one. Now see, it says a circular metallic rod of length 250 mm is placed between two rigid immovable walls as shown in the figure. The rod is in perfect contact with the wall on the left side and there is a gap of 0.2 mm between the rod and the wall on the right side. If the temperature of the rod is increased by 200 degrees Celsius, the axial stress developed in the rod is, so in this case, see, there is a gap. So see, we can memorize the formula, which I do not recommend you to. So what we can do, we can try the basic principle. So we understand that the thermal elongation, that is alpha delta T into L, alpha delta T into L plus or minus sigma thermal L by E, it is equal to lambda. So that is zero point 0.2, the gap is 0 0.2. Okay. So from here, we can definitely calculate the thermal stress, isn't it? Okay. So what we can do, so we can put all the values here. So alpha is what? Alpha is given as 10 to the power minus 5. Okay. The temperature is increased by 200. Okay. L is how much? 250 mm. Okay. Please take care of the units. Right, minus sigma thermal L is 250, Young's modulus is 200 GPa, so 200 into 10 to the power 3, and this is zero point 0.2. Okay, this is zero point 0.2. So definitely when we'll be solving this equation, when we'll be when we'll be doing the calculations, we'll get the answer, right? So when we do that, what we'll be getting, I'll just give you the final answer. So sometimes see these questions might be seems very calculative to you. Okay, but the thing is that that this is see I'm telling you all these questions so as you can you know relate. Okay, so if a question, so for understanding of the concept, that is why we are doing all this question. So when you solve from here, you will be getting the thermal stress as 240 megapascal, and this is going to be in the negative. This is going to be in the negative one. Okay. Okay. Now let's try one more question. Okay, so let's try one more. Let's see if we can do this one. So see, sometimes they might twist the question also to some extent. One interesting question is there. Just I'll just a moment, guys. Okay, this is the question. Huh? Let's try this question. I'm very sure we can do. Please go for it. Please do it. Yeah, please do this question. I'm very sure we can do it. Please try to do. I'm very sure we can do it. Please do it. So now what does it say? So we have alpha that is 12.5. We have alpha that is 12.5 into 10 to the power minus 6. E we have, now it says if the rod fitted is strongly between the supports as shown in the figure is heated, the stress induced is due to this will be. So what is going to be the stress? Okay. Now first of all, please try to understand the question. Now in this we are having a bar, and to one end of the bar there is one spring, and to one end of the bar there is one spring attached. Okay, there is one spring attached, right? Now, when you see this spring, so see, when you are going to increase the temperature of this particular assembly, this bar of zero point 0.5 meter length is going to show some expansion, right? Okay, but there is support on the other end, and also a spring is attached. So, by what amount do you feel? By what amount do you feel that this stretching is going to happen? So definitely when it is going to, when you are increasing the temperature of this thing, when you are increasing the temperature of this thing, what is happening? The spring will get compressed. So let's suppose the spring is compressed by X. Now so what we can say? So again we can do the same thing. So we can say alpha delta T into L, alpha delta T into L, and now this reaction will come. So minus sigma thermal L upon E, and this has to be equal to the expansion of the spring, isn't it? This has to be equal to the expansion of the spring. Do you agree to it or not? Yeah, definitely, sir. It has to be equal to the expansion of the spring, right? It has to be equal to the expansion of the spring, right or wrong? Yeah, definitely, sir. It is going to become equal to the expansion or the contraction of the spring. Okay, now what we can say? So now the sigma thermal is also we know. So it will be, so see, if the load is acting here, so what will be the sigma thermal? So if the spring is deflected by x, if the spring is somewhat deflected by x, so when the spring is deflected by x, my dear, so when the spring is deflected by x, so what would be the force in the spring, or what will be the stress in the body? So see, if the stiffness of the spring is given and the deflection is given, it will be K times X, isn't it? L upon E is equal to X. Do you agree or not? Upon area, because stress is force upon area, isn't it? Yeah. Now from this equation, let's see what we are having. So we are having alpha. We are having this alpha. Alpha is 12.5 into 10 to the power minus 6. What is the change of temperature? So the temperature is changed by 20 degree. What is the length? Length is 500 mm. Okay, minus K. So K is kilonewton per meter. Okay, kilonewton. So I'll do everything in meter then. Right, see, why to unnecessary take risk? Right, so this is 50 kilonewton. So 50 into 10 to the power 3 x. This is 0.5 upon area. So the diameter is also given, that is pi by 4 into pi by 4 into this d, that is 10 square, right? Yeah. So now this will become, what is the Young's modulus? Young's modulus is 200 GPa. So 200 into 10 to the power 3 is equal to x. Now see, from this equation you have only one variable, and that is your x. So when you calculate x from here, you are going to get 0.125 meter. You are going to get 0.125 meters. So what is going to be the thermal stress, guys? So we understand that thermal stress is kx upon A. Now K is there with you, 50 kilonewton per meter, that is 50 into 10 to the power 3. What is x? X is 0.125, and what is the area? It is pi by 4 into 10, that is 0.01 square. 0.01 square. Okay. Now in this also you have to do that. Now this is divided by 1000 square, because when you are putting, and this is also 10 to the power 9 then, because this is 200 GPA now. So I have converted everything to meters. So we need to convert it into meter also. Okay. So you have to be always careful about, you always have to be careful about the units while you solve the question. That is of utmost importance, right? Okay, very well. Now let's try one more question, and we'll then conclude the thermal stresses, right? So I hope you have understood the concept of thermal stresses in this. Okay, so let's try this one. Very interesting. Okay, let's try this one. Let's try. I'm very sure we can do. Please do, guys. I'm very sure we can do. Please try to solve this one. Very interesting question. So now we are taking the thermal stresses to 3 dimension also. We have seen it in 2D. Now we are seeing it in 3 dimension also. Please go for it. All the live students, you may please try this question. Yeah, hello all in one. Welcome to the session. My name is Dr. Shankar Sir and we are dealing with the thermal stresses. So, have you tried this question? What is the answer to this question? Can you please try this question? Please do it. So, see guys, how we can do it. So, in this case, it says a cube having the side of length A is constrained in all direction and is heated uniformly so that the temperature is raised to T degrees Celsius. If alpha is the thermal coefficient of expansion of the cube material and E is the modulus of elasticity, the stress developed in the cube is. So see, we are having a cube here. Okay, let me make it. Okay, so see, very simple. The same concept we have to apply now. What we have learned, that is the superposition. Okay, in this part of physics, superposition is very useful. Now see, so we are having some sort of a cube, okay, and it is restricted to expand in all the direction. So now if I increase the temperature of this whole thing, if I increase the temperature of this whole thing, what is going to happen? It will try to expand in all the directions. So when it is trying to expand in all the direction, there will be a reaction coming from all the directions. So there will be R here, there will be R here, there will be R here. Okay. Now to apply the concept of the superposition, what we need to do? So we need to do what? Sir, we need to use the superposition in one direction. Okay. So now let me take the x direction. You can choose any direction. So if I write the x direction, so what is happening in the x direction? Please try to realize this. Now see, there are four things here. Okay. One is the change of temperature is there. Then there is the load in all these directions. Okay, so we are having this load, this mechanical load in x direction also, in y direction also, in z direction also. So I have to see the effect of each of the load in x direction. Okay. Now if I raise the temperature by delta T, what is going to happen? It will be alpha delta T into L, or the dimension of the cube is A. Then so this is positive. This would try. So only temperature if I see. So only temperature when I see, it will be alpha delta T into A. It will be alpha delta T into A, right? Alpha delta T into A. And now what is going to happen? So now due to this R, if I see this R, this will be a compressive. So this is minus RA upon A, right? Minus RA upon A. Now you are seeing this. Now when you are seeing this, so see, when you are applying the superposition, you are seeing that one effect, you ignore all the other effects. So you are only seeing the one effect, you are not seeing the other effects. So when you are seeing this effect only now, when you are seeing this only now, you are not seeing this, you are not seeing this, you are not seeing the temperature. Now due to this one, this R, see, it is compressive in y direction. So what will be its effect in x direction? So it will go in positive, okay, and it will become mu RA upon A. See, why sir it is like this? So see, in so if we observe this R, the load in the y direction, x direction will be lateral for it. And for the lateral dimension, what happens? For the lateral dimension, Poisson ratio comes into play, right? So it will become mu RA upon AE, right? Now you are going to see this one, okay? You are going to see this one. You are not at all concerned about any other R. Now when you are seeing this only, what is its effect? So this is Z direction. So it is compressive in Z direction. It is contracting. It is doing the contraction in Z direction. So its effect in the X direction will be of expansion. That is the Poisson effect. Every longitudinal strain is connected with or is having two lateral strains but in opposite direction. So what is happening? So this R, due to this R, what is going to go? Now due to this R, you are going to see that it will become positive. When its effect you are going to see in the x direction, so this will become positive. And since you are seeing the lateral direction, a mu will come, a Poisson ratio will come. So it will become plus mu RA upon AE, and this all becomes 0 in x direction. Now from here, can we write, see, like this, alpha delta T A. So A is gone, every A is gone, so it will become alpha delta T, and this will become minus sigma thermal upon E, R by A, plus and mu plus mu, that is 2 mu, and sigma thermal R upon A is sigma thermal upon E is equal to 0. So from here, can we write sigma thermal as alpha delta T E upon 1 minus 2 mu. So this is going to be your thermal stress. This is going to be your thermal stress. So it will become the B option. So see, in the case of the cube, that is a 3D geometry, also we have learned that how we can calculate the thermal stresses, right? I hope this is fine to everyone. Now please observe. Okay, now let's observe. So now let's suppose we are having a composite arrangement. We are having a composite arrangement. Now when we are having a composite arrangement like this, let's suppose we are having a composite arrangement. So we are having the steel, we are having the copper with us. So we are having this as the steel is there. Let's suppose this is copper, okay? Steel is there, copper is there. So now when we are having the steel, when we are having the copper, and they are, arranged in the composite way or the parallel way. Now in this case, the temperature of this whole assembly is increased. Now when the temperature of this whole assembly is increased, the first question of mine is, will there be uh, ultra, my dear, I am right now teaching the thermal stresses. Do you have any problem in this? Like, are you not getting what I'm trying to teach you, guys? It's been a long session. Already 4 hours, 10 minutes are there. So I'm trying to complete this whole properties of solids. Okay. At least I'll just, after this, I'll explain the strain energy part also. Is there any problem? Please tell me. Yeah. Okay, you are in 10th. Okay, okay. So you want to go ahead with the NEET examination. So it's a very good thing, my dear. Since you are so, like you are coming and you are seeing the physics session. So that is a very nice thing. And definitely, अभी आप 10th में हैं तो कल 11th में भी होंगे. So this is going to help you. I, I am doing my duty, my dear. Okay, if somebody is watching it or not watching it, that doesn't, you know, I'm trying to do my part. Okay, and there are some students who watch the recorded of it. Okay, anyways, see, this is something, the channel is new only, and we are trying from our side that to help the students as much as we could do. This is an Unacademy channel. Okay, so anyways, so now see, when these two are there in a composite structure. Okay, copper and steel are attached in composite things. So when we are increasing the temperature of it, what is going to happen? Will there be any stress in this or not? The first question is, will there be any stress in this or not? So what is our concept? So the concept is, whenever something, some material is restricted, right? Whenever some material is restricted, there will be some stress in that particular material. Okay, now in this case, is there any restriction? It is not fixed from any end. Now when I say so, many students think that, so since there is no restriction, when we increase the temperature, there will be no stress. So it is not like this. Now please understand this. So previously we have learned that what is composite bar, what is the condition of a body or a arrangement of system being composite. So the necessity is that both of it, the necessity is the both of it must be having, both of it must be having both the materials must be forming a composite. That means they must be together at all the times. They must be together at all the times. Okay. Okay. Right. So now when I increasing the temperature of it, now you please tell me, so steel and copper both are different materials. So when both are different, they must have some coefficient of thermal expansion. So let's suppose the coefficient of thermal expansion for steel is alpha steel, and for copper it is alpha copper. And generally see, the non-ferrous materials have more value of coefficient of thermal expansion. See, obviously, when you see the difference of whenever a temperature is changed, okay, oh, you play chess? I do also play chess. You find me on chess.com, we will play together. No worries. Okay? Okay, anyway, so when I increase the temperature of this assembly, just a moment. Yeah. So when we increase the temperature of this assembly, since the coefficient of thermal expansion is different, so individually, if nothing of them as individually, so see, when the temperature of this whole thing is increased, since their temperature, since their alpha is different, coefficient of thermal expansion is different, they must be showing different expansions. They must be showing the different expansions, right? If they are alone, if they are not in the composite arrangement, they would have expanded differently. Okay, like for example, since the coefficient of thermal expansion of alpha is more, so it tries to expand more. It tries to expand more. Okay, okay, but it and also for steel, if the coefficient of thermal expansion of steel is less than the copper, then if it is alone only, it would have expanded less. It would have expanded less than that of the copper. But can this thing happen? No, sir, it cannot happen, because if the things are happening this way, if things happen this way, this wouldn't be a composite structure or composite system anymore. It can't be a composite system anymore, because for it to remain in the composite structure, they must be together always. Okay. What is the condition of some arrangement being composite or being parallel? So they must not be separated. They must be together. Okay, they must be together. Okay, so when their coefficient of thermal expansion is different, individually they would expand differently. Okay, now if their deflection or elongation or change in dimension is different, they cannot remain together and hence cannot be a composite system. So for them to be in the composite system, they must deform the same. They must deform the same. Now, please understand this. So for them to deform same, there can be three ways for it. There can be three ways for it. One way could be that steel expand more and reaches the level of expansion of the copper, or the copper deforms less and reaches the expansion of the level to the steel. Or one way could be that some elongation steel could do and some contraction copper could do, so that they reaches the same level. Okay, now you please understand them as two friends. Okay, if two friends are there, so how the friendship is sustained, how the composite of the friendship remains. So as I always say, see, all the materials, everything, they are like us only. Okay, they behave like we do, right? Now if you are having a friend and see, two friends are there and they want to maintain their relationship, so they have to, both of them have to make a little adjustment. If one expects the other to make all the adjustments, the composite is going to break, right? This is how life works, isn't it? Okay, this is how the life works, right? Now, steel, what will happen to steel? Now, to maintain both of them in the composite structure, what is going to happen? Steel will have some more elongation and copper will have some contraction. Okay, now for steel to move ahead, steel to have more elongation, what kind of stress must come in the steel? Steel must have so since it is elongating, it is having tensile stress, right? So why the stress is coming? Because there is restriction. What is the restriction? That they have to elongate equally. They have to deform equally, right? Now similarly for copper, so since copper coefficient of thermal expansion is more, so it has to reverse back. So it has to contract. Now when it has to contract, it has to move in this direction. It must have some compressive stress. It must have some compressive stress. So basically from here what we come to understand, so when two materials or when two bodies of different materials are becoming or are arranged in a composite system and the temperature of the whole assembly is increased, there will be some stress in individual constituent of that composite, because that coefficient of thermal expansion being different, and they ultimately have to elongate by the same amount, they ultimately have to have the same, deformation. Understood? So see what we come to know. So the if two materials are arranged in composite, the material having higher coefficient of thermal expansion will have compressive stress, and the component or the material which is having lower coefficient of thermal expansion will have the tensile stress. I hope it is fine to everyone. Okay, I hope it is fine to everyone. Right? Okay, so we are having it like this. Now, if I write the equation, now let's see. Let's write the equation. Okay. So see, we are having this steel, we are having this copper, we are having this copper. Now when the temperature is increased, the steel has elongated less, the copper has elongated more. The copper has elongated more, right? This is your copper. And now for them to have the same level of elongation, the steel is moving ahead and the copper is moving backward. So that the ultimate elongation of the steel has to be equal to the ultimate elongation of the copper. Ultimate elongation of the copper. So what is the net elongation of the steel? It is alpha steel delta T into L, right? Plus, so since it is having the tensile stress, so I am adding R L upon area of steel, Young's modulus of steel. So why I have added it here? So I have added because steel is having the tensile stress. So tensile we take as positive. Now see, for copper, what is going to happen? So for copper, it is alpha copper delta TL, alpha copper delta TL. Now I'll be using the subtraction sign and minus RL upon area of copper, Young's modulus of copper. Okay, now from this very equation, you can obviously find R. Now once the R is fine, you can see the stress in both of it. So the sigma copper will be R upon area of copper because stress is load upon area, and sigma steel is going to be R upon area of steel. I hope it is fine to everyone, right? Yeah. So now this way again you have used ultimately the superposition theorem, and you have got the stresses in both of the materials of both of the bodies of the composite. I hope it is fine to everyone. So guys, now thermal stresses is also over. So in this session till now we have seen the Barson series, we have seen Barson series, we have seen the thermal stresses, right? Okay, so these two things we have seen till now, and we have solved a lot of questions, and we have understood, I hope, the whole concept very well. Now we have one more concept to go in this session, that is the strain energy. Okay, that is the strain energy. Okay, okay, so what is the strain energy? So I'll just okay. So now we are going to begin with the strain energy. So it's quite a long session. I am teaching continuously from last 4 hours 30 minutes. Okay. So let's do one thing. Let's have a 10 minutes break, and we'll resume the class at 5:45. Okay. I'll just resume the class at 5:45. Okay. Okay. So since it has been a long session, so I need a 10-15 minutes break. So I hope it is fine to you, right? So in this session till now we have done with this, thermal stresses, and we have done with the bars and series concept. So I'll just have a 15 minutes break, and afterwards we'll continue. Okay, so let's continue with the strain energy. Okay, so let us start with the strain energy now. Okay, now see, what is the strain energy, what is its relevance, and how it influences the properties of the solid and how it affects the world of the physics. So see, strain energy. So basically, it is said to be. So how can we firstly understand the strain energy? So basically, strain energy is the energy which is said to be stored, which is said to be stored, which is said to be stored in a body, in a body when load applied on the body, when load applied, or we can say when the work done by the load, when the work done by the load on a body deforms that body, deforms that body. Okay, so see what happens in this, see what is the meaning of it. So whenever there is a load on somebody, whenever there is a load on somebody, there will be some work done by that load. Okay, and if that work done has the effect to deform that particular body, we say the strain energy is stored within the body. Okay, now for having any movement in a body, there must be some energy to it, right? Now see, we have seen something. So when we stretch a body, when we stretch a body, when we deform a body, and when we unload it, many times it happens that it recovers its original shape and dimension or size. Okay. Now for it to regain its original shape and size, it must have some energy in it, right? So that is one form of the strain energy, right? So due to the strain energy being stored in a body, it can have some effects on the physics, like due to this stored strain energy, one can regain its original shape. Okay, okay, or it can deform to a long, like for example, ductile material have more strain energy storing capacity, right? This is how it happens. So see, whenever, so see, in simple words, whenever a load is acting on a body and it deforms that body, some form of energy is getting stored in the body, and that is what we call as the strain energy. Okay, and obviously, like energy, we know from the first law or the law of conservation of energy, that energy cannot be created, cannot be destroyed, but it can be transformed from one form to another form. Now, when the strain energy is stored in a body, obviously it is converted from some another form of energy, and that is the energy of the load in the form of the work done by the load. Are you getting my point? Okay. So strain energy is the energy which is said to be stored in a body when the work done by the load on the body is deforming that body. Okay. Like for example, now see, please understand it. So now we are having, let's suppose, a body. Okay. And on this body there is some load applied. Okay. There is some load applied. Right. Now, what is going to be the work done by the load? What is going to be work done by the load? So, the work done by the load is going to be how much, sir? It will become half P into delta. Sir, why you are taking this half P into delta? So, work done is obviously what? Work done is obviously force into some sort of a distance. So, see, in general, what is work done? In general, what is work done? So if we have a force versus displacement curve, if we have a force versus displacement curve, we say that work done is force into the dx. Okay, so if some force is acting, there will be some displacement. Let's say the displacement is dx, so that will be the work done in this dx portion, right? Right. Okay, now same way, see, now if this, if this displacement is like a straight line, if a body displaces like this, so you find this area and you get the work done. Okay, this area gives you the work done. Okay, so we very well know this thing that area under force versus displacement curve gives you the work done. Now in the same way it happens here. So see, when a force is applied on a body, it starts as deflection. Okay, and how it happens, how the deflection happens. So let's suppose on this y-axis I am having the load, and on this axis I am having the deflection. Okay, I am having the deflection. Now when the load is applied on this body, it is, let's suppose this load is increasing. Okay, it is increasing, bit by bit. So when this load is increasing, the deflection will also increase. So it goes like this. Okay, it goes like this. When the load is increasing, the deflection also increases. So when the load is increasing, deflection is also increasing to some point. Let's suppose this is P, this is delta, this is P, this is delta. So what is going to happen, guys? So now you are going to see that this area, in the same way we get the area of force into the displacement diagram. Okay, so the same way we can have the area here. The same way we can find the area here. And see, whenever you are making load versus deflection curve for any material, it is initially like this only. Okay, so it makes a triangle. So when it's making a triangle, you can say that the work done here is half P delta, and this is nothing but the strain energy. This is nothing but the strain energy, so we'll call it U. So simply see, when there is a body, okay, when there is a body, okay, having subjected to a load P, okay, having the length of L. So what is going to be the strain energy in this body? So the strain energy, that is U, it is going to be half P into delta. It is going to be half P into delta. I hope this is fine to everyone, right? Okay, so the strain energy is going to be half load into the deflection, half P into delta, right? Half P into delta. I hope it is fine, right? Now see what we are going to do. So what we are trying to do now, so we will be generalizing this concept. We will be generalizing this thing. Sir, how we are going to generalize this thing? Now let's observe. Okay, so why we are generalizing? So see, there can be many cases, isn't it? There can be, self-weight also, there can be anything. So I'll just generalize this. So see, let's suppose there is a body like this, and we are having some load, some axial load on a particular section X. Okay, let us take in section X, and this is the length L. Okay, now this section X, so I'll take one strip. Sir, why you are doing this? See, because now in this case, the load is constant. So we can work with this formula. But there can be different cases also. Na? What could be the other cases? So, Young's modulus can vary with length, isn't it? Right? Area can vary with length, right? Okay. Also, load can vary with the length. Load and area both can vary with the length. Okay. In all these cases, guys, the strain energy, we cannot apply that formula directly. We have to do something different. See how we are going to do it. Now see, whenever something is in variation, we understand that we need to take the strip. So we have taken the strip, and I'll be writing the strain energy of that strip. Okay, so how I'm going to write the strain energy of this strip? So the load, let's suppose, on the strip is Pxx. Okay, the length of the strip is dx. Okay, upon what is, so see, what is the formula we are applying? So see, strain energy of the strip will be half Pxx into delta xx, that is elongation of this strip, isn't it? Okay, so how we can write it? Can we write it like this? Du is equal to half Pxx, okay, Pxx, and delta xx will be, so it will be load into length. Length is the length of the strip, dx PL upon AE, area of x and Young's modulus of x. So can I write it like this? Area of x and Young's modulus of x. isn't it? Okay. Okay, so now if I write this equation like this also, so du is equal to half pxx square, half pxx square dx upon aexx, upon aexx, right? Okay. Okay, now from here what we can do, so if I integrate this relationship, this is the general expression I have made for you. So it is integration pxx. So if I integrate it between 0 to L, I'll getting the, so it is 2 times aex dx, 2 times aex dx. So this is going to be your strain energy generalized. So okay, so we see we can use this formula for each and every cases. Okay, so if we can see this formula, we can obviously memorize this formula and we can use it for every case of the axial loading. Okay, and if the force is applied in the form of shear force, also in the form of bending moment, maybe in the form of turning moment, that also some similar sort of equation you can use, right? Like for example, see, I'll just tell you. So in the case when there is axial loading, right? Like in the case of self weight, or in the case of axial load, all this comes under the category of the axial load, the normal load. There can be case in which bending moment is applied on a body. Okay. There can be case in which the turning moment can be applied on a body. Turning moment can be applied on a body. Okay. Now see, when the axial load is there, what is the formula? So the strain energy is going to be 0 to L pxx square dx upon 2aex, right? See, very, very simple, right? Now similarly, see, in the bending moment, you will see the analogy. There is similar analogy. So 0 to L, so see, in the case it will become bending moment, that is mx square dx upon 2ei. I is the area moment of inertia, and for turning moment it will become u is equal to 0 to L, 0 to L txx square dx upon 2ei. Okay, txx square dx upon 2ei. So for each kind of a loading, you are having a similar set of formulas. So if you remember one, obviously you will be able to remember the other two also, because we are having quite a simple analogy between all these formulas, right? Now see, what is going to happen. Now see, if we memorize this formula, I can deal with any case, right? Like for example, if it is asked to you, like there is a body on which a pure axial load is applied. Let's suppose we are having the pure axial load on the body. So when we are having the pure axial load on the body and length of this is L, see what you have to do. Sorry, we have to use this formula. So 0 to L pxx square dx upon 2aex, right? 2ae, and this is your xx. Okay, so the strain energy will become 0 to L. Now if I take a section x here, if I take a section x here, at a distance of x from the bottom, okay, what will be the load at this section? So it will become P only. So this is P square dx upon 2aexx, right? Okay. Now at xx the area is also ae is also constant, so I can write it like this. Okay, so we have seen the loading diagram now. So see, when there is only one load at the end, throughout the section it remains the same. Okay, so whichever section, whichever point you see, you will have the same loading, right? Now see, what is this going to become? It will be 0 to L p square dx upon 2ae. Now if I integrate this relationship, what I'll be getting? I'll be getting p square L upon 2ae, because see, p square, p is also constant, a is constant, e is constant. So we are having p square L upon 2ae, that is your strain energy. I hope that's fine to everyone. Now let's suppose we are having a bar, a uniform prismatic bar. We are having a uniform prismatic bar of length L, okay, of length L, and at a section XX. So this is the prismatic bar and it is having a self weight of gamma, that is kilonewton per meter cube. Okay, it is having a self weight of what? It is having a self weight of gamma. Right now, when it is having a self weight of gamma, I want you to find me the strain energy in this case. Can you tell me the strain energy? Please go for it. Please give me the strain energy in this case. The live student can answer me. Please try, guys. I'm very sure we can do. See, in the same concept, you have to do it. You may please try. What is the strain energy stored in a prismatic bar due to self weight? Please try to do it. The live students, I'm very sure we can do. So you must try to solve the question. See, if you try it, I'm very sure we'll be able to do. Please try doing it. See, again what you have to do guys, you have to use the very same formula, right? You can use the very same formula. So what we know, sir, is strain energy is 0 to L P xx square dx upon 2AE at section xx, right? Now please try. I'm very sure we can do. The same formula, you need to figure out what is the load at xx section and you can try it. So how we can be doing it? So see, what we have to do, so we have to put the load at the xx section. So what will be the pxx in this case? So this is gamma. So this will become gamma into A into x. So strain energy will become 0 to L gamma Ax square dx upon 2AE, right? Okay, so what will be the strain energy then? So it will become 0 to L. This will become gamma square A square, and this is going to be gamma square A upon 2 E and x squared dx. So what will be the strain energy then? So it will become, strain energy will become strain energy will become gamma square. So gamma is constant. A square by 2E. Okay, and x square integrated, it will become L cube by 3. So U will become gamma square A L cube by 6E. Okay, gamma square A L cube upon 6E. I hope it is fine to everyone. Right? Now, sometimes they give you this in the terms of the self weight. So, you remember WF. So, when we were finding the elongation in the last session, I have told you that in the self weight they give the information two ways. One is like they give you the weight density, and the way is that they give you the self weight in kilonewton. So when they give you something like this self weight is gamma AL. This self weight is going to be gamma AL. So what is going to be if I write if I try to write it in this term? So see, it will become, see, I'll just replace the gamma with W by AL. So it will become gamma square will become W square, A square, L square, and this is A L cube. Okay, so this is obviously the L is same only, na? Yeah. So this is a small L capital, same thing. So see, I'll write gamma is equal to W upon AL. So this will become W square upon A square L square A L cube upon 6E, right? So this will become W square L cube upon 6 sorry, not L cube, W square L upon, see, W square L upon how much? So W square L upon, so 1E will be cancelled out. So 6AE. Understood, beta? Understood? Please tell me if it is fine to everyone or not. I hope yes. Okay. Right. So see, in this way, you can get the elongation due to self weight also using the same formula, the same concept. Right. Now, if I ask you, so when we were finding the elongation, we have seen something also, the conical bar. Now, if I ask you that what will be the strain energy in a conical bar, how you can do it? Let's try to solve it. So let's try to find out the strain energy in a conical bar due to self weight. Okay, so let's first take care of the strain energy calculation. So strain energy strain energy in a conical bar, strain energy in a conical bar due to self weight. बताइए, let's try it. ठीक है, so let's find the strain energy in a conical bar ड्यू टू सेल्फ वेट. तो सेल्फ वेट की वजह से कोनिकल बार में कितनी स्ट्रेन एनर्जी आएगी? लेट्स ट्राई इट. आई एम वेरी श्योर वी कैन डू. प्लीज गो अहेड. प्लीज डू. Please try to do it. I'm very sure we can do. Please go ahead. Let's see if we are able to do it. Very interesting. See, when you know the basic, you can deal with any problem. Please try to deal with it. Please do. So see how we can do it. So in this case also, which formula we must apply, guys? Which is the formula that we must use in this case? So sir, we must use again this formula, right? Strain energy is going to be equal to integration 0 to L Pxx square dx upon 2ae at section x, right? Right now, if I assume, let's suppose if I assume the area, okay, here as a, if I assume the area here has a, so what is this pxx in this case? So sir, pxx is gamma a x, so I'll be taking the x from the bottom again, and this is your L. Okay, this is your L. So this will become Pxx is gamma Ax upon 3. Sir, how come? Because see, gamma multiplied with volume. So since it is a conical, so for conical it is 1 by 3 of area into x, right? So now let's put it here. So we'll be getting a strain energy 0 to L. So what is Pxx? Ax upon 3 whole of a square dx. Okay. Now please observe something. Now see, E is constant, but is the area independent of the x? Is the area here is independent of the x? No sir, area is not independent of the x, because see, we can see that the area is changing with x. So if I assume, so I'll write it here A1, let's write A1, because this is the area of, let's suppose this section, so I'll just write it at 1, A1. Why sir you are writing this A1? Okay, why you are writing this a1? So because see, I want it to be differentiated from this a is the area at the fixed end. Okay, now at some x I'm assuming the area to be a1, so I'll write it here a1 only. So see, if I open up this bracket now, first of all, so that I'll see something. So integration 0 to L, it will become gamma square a1 square x square upon 9, gamma square a1 square x square upon 9, okay, into 2, and this is e times a1, dx, right? E times a1 dx. So see, a1 and a1 will be cancelled out. So let me take all the constants outside the sign of integration. So when I take all the constant outside the sign of integration, so gamma square is a constant, this will become 18, E is a constant, and what will be left inside? Sir, A1 and x square. A1 will be left inside, isn't it? Sir, why A1 is being left inside? Because A1, what I am referring to, A1 is the area at this section XX. Now when A1 is the area at the section XX, so what is happening? A1 is the area at section XX, so obviously it depends upon X. So whenever you are integrating, whatever is dependent upon the X must be inside this bracket. Okay? Must be inside this bracket. Okay? Okay, so now here the area is A1, so it will become A1 upon X, and this is A upon L. Okay, so A1 is what it is, AX upon L. AX upon L. So this will become, strain energy will become gamma square upon 18E. Okay, and this has become 0 to L A. See, not, oh sorry, my mistake. Just one moment. So see, it is not like this now, because see, this is area, not the dimension that we can apply. So see, if let me assume that the diameter here is D1 and the diameter here is D. So can we write, see, can we use the similar triangle funda? Can we use the similar triangle thing? So what is the similar triangle thing? So can we write d1 upon x is equal to d upon L. d1 upon x is equal to d upon L. Right? Okay. Okay. Now a1 upon a. This will become what? This will become d1 square upon d square. Isn't it? d1 square upon d square. Isn't it? Do you agree or not? Right? And d1 by d is what? Sir, see, why it is? Because, sir, it is a circular conical bar. Na? It is a circular conical bar. So when it is a circular conical bar, the area at any section will be pi by 4 d square. Isn't it? So pi by 4 will be cancelled out and it will become d1 square. Right? A1 d1 square. So see, d1 by d is x by L. So can we write from here? Can we write from here that, sir, a1 by a, now see, a1 by a is equal to x square by L square. Can we write like that? Yes, sir, we can write like that. So now I can replace it. So a1 is so it will become gamma square 18e 0 to L. So a1 will be a x square L square. So it will become x to the power 4 L square dx, x to the power 4 L square dx. So this will become, strain energy will become gamma square a upon 18e L square, 18e L square, and this will become 0 to L x to the power 4 dx, x to the power 4 dx. So this will become gamma square a, and this will become x to the power 5 upon 5. So 18 into 5, 90 e L square. So what it will become? It will become gamma square a L cube upon 90 e. So this will be the strain energy in the case of the conical bar. Is it fine, my dear? Please answer me. Is it fine, my dear? Please give me a yes or no. Right? Yes or no? Please answer me, guys. Yeah? Please answer me. Okay? Wonderful. Wonderful. So see, we have seen from the same formula the self-weight case, now the conical bar case also. Similarly, you can find this, you know, the tapered bar case also you can do, okay, in the same manner, right? So now let's suppose we are having, yeah, now let's suppose we are having what? Let us suppose we are having what? So we are having